Great pleasure that we extend a warm welcome to all of you to Winter School 2023, jointly organized by the Center for Development Economics, Delhi School of Economics, and the Econometric Society. We are honored to have with us the distinguished presence of Professor Ram Singh, the Director of Delhi School of Economics, Professor Rohini Somanathan, the Head of the Department of Economics at Delhi School of Economics, Dr. Manish, the Executive Director of Center for Development Economics, Professor John Wooders from NYU Abu Dhabi, and our esteemed chair for the session, Professor Pulin Nayak. Now, I would like to hand over to Professor Pulin Nayak.
We will start with Colgate, University Colgate, and then you can invite me to speak.
Okay. So I would like to call Ms. Nanika Nandi on stage for the university anthem, and I request everybody present to stand up for the same. Please take your seats. Now, I would like to hand over to Professor Ram Singh.
Distinguished speakers of plenary sessions, good morning. Distinguished speakers of the plenary sessions of Winter School 2023, organized by Center for Development Economics at Delhi School of Economics, jointly with the Econometric Society, session chairs, colleagues from University of Delhi and other institutions, and participants in the Winter School. A very good morning to all of you. I wish to say a few words about the Delhi School of Economics, popularly known as the DSE. DSE was set up in 1942 as a Center for Excellence in Social Sciences, with Professor V.K.R.V. Rao as its founding director. The DSE started with Economics Department as a nucleus and comprises of departments of Geography and Sociology along with Department of Economics. The school also boasts of Ratan Tata Library, that is a very rich collection of books, journals, and research being done that has been done at DSE. Since its inception, the DSE has been known as a premier institution of advanced learning and research in India. Its constituent departments, every single one of its constituent departments are known or appreciated worldwide for the academic standards they maintain, the teaching and research techniques they impart to their students. In its 75 years of its journey, the school has, alums of the school have made their names in all walks of life in this nation. They belong to who's who list, whichever walk of life you look at, especially disciplines related to economics. This year happens to be 75th year of the DSE. Therefore, this winter school is special. And winter schools are an important part of academic activities at the Delhi School of Economics. I'm sure this winter school 2023 will turn out to be a huge success. It will be a learning and pleasant experience for the participants. I wish the school very best. Thank you. I now invite Professor Rohini Somanathan, the head of economics department, followed by executive director of CDE.
Thank you for all being here. The winter school is sort of an amazing thing for us. It's just remarkable every year that a public university with many, many constraints in funding, in personnel and administration can actually pull this off. And it's been happening for 2 decades now. And it just wouldn't have been possible if the Winter School Organizing Committee every year didn't throw themselves into it. And if the speakers that we invited every year were not so gracious to come all the way across the world, and there are many, many places you could be. And so thank you warmly for being here with us. We really appreciate that choice. I hope this is a beginning for those of you who are here for the first time, and that you'll find ways to connect with us and repeatedly connect with us. I hope that the ones that are coming back who've studied here will have a good time and you'll keep coming back. So all the best. Let's have a wonderful 3 days. And thank you so much for being here.
Since I'm still learning, so I will be using a script. So my speech is very much scripted. So respected colleagues, dear students and fellow researchers, I welcome you all on behalf of Center for Development Economics, Delhi School of Economics. The Winter School of Delhi School of Economics has been hosting a series of lectures by some of the world's leading economists for over 2 decades now. Since 2018, the event is being organized in collaboration with Econometric Society. This year, we have 3 eminent academicians with us, Professor John Wooders, Professor Jody Gali, and Professor Joel Mukir. The lectures and informal interactions with visiting scholars have been an extremely useful source of knowledge and capacity building for our faculty and students. The conference also hosts young scholars selected from across the country through a highly competitive process. In fact, this year, all faculty members at the Department of Economics devoted a lot of time and energy to read about 250 papers and then selected less than half of it for presentation at the Winter School. Selected scholars get the opportunity to attend invited lectures and present their research work. The benefits of the Winter School extend to the wider research community based in India and abroad. The Winter School is an annual flagship event of the Center for Development Economics. The Center for Development Economics was established in 92-93 with support from Ministry of Finance, Government of India. The objective of CDE is to promote and disseminate research in the field of economics. With the help of our students, researchers, and faculty members, CDE has contributed greatly to the existing knowledge system, especially in the field of economics. I am confident that Winter School 23 will be valuable contribution to this tradition. I thank the wonderful team of Winter School Committee led by Professor Ram Singh, Professor Somendu Sarkar, Professor Devesh Birbal, Professor Sandeep Dattan, Professor Swati Saini. I am aware that they have spent much of their time over the last few months in visualizing and bringing this event to life. I also thank Professor Mosmi Das, Dr. Satendra Gupta, Dr. Ritika Garg for their help in initial preparation of the Winter School 23. Especially Professor Mosmi Das for helping us to invite a wonderful academicians from different parts of the world. CD is grateful to Professor Pami Dua, former director of the Delhi School of Economics, and Professor Surendra Kumar, former head Department of Economics, Delhi University, for their constant guidance and support in organizing the Winter School. Lastly, no program is successful without the active participation of our students. We are grateful for them. I once again welcome you all. I am sure you will have a wonderful and memorable time here. Thank you. Thanks a lot.
We will now start the first plenary session. I request Professor Pulin Nayak to chair the session. We will take a minute to shift the layout of this place will be different. Give us 1 minute.
Thank you very much. Thank you. Thank you.
Someone can help you get rid of it.
Oh. Thank you.
Okay. A very warm good morning to everyone. It's wonderful to be here. Possibly around the 30th year after the first winter school was started. I think, if I recall right, it was either 92 or 93 that we had the first winter school. And let me also say that I had the good fortune of being very much in the thick of things in organizing the first winter school with my earlier colleague, Professor Kaushik Basu, known to most people sitting here. And this is the 30th year, so it's absolutely wonderful. And we have these three. Here we are, the very first plenary session. The three scholars we have already mentioned, Professor John Wooders, Professor Jordi Gali, and Professor Joel Moquet, sitting here. A warm welcome to all of you, and very many other scholars who will be here presenting their own research and mixing with faculty here and students. So we'll move on pretty fast. I'll just take a few minutes, just a minute or two, to introduce Professor John Wooders, who is known to most people working in the area of game theory, behavioral economics, and experimental economics. But let me nevertheless speak a few words about Professor Wooders. He is a professor at the New York University, Abu Dhabi, yes. PhD from Cornell University, 1992. Co-director, Center for Behavioral and Institutional Design and the Social Science Experimental Laboratory. Fellow of the Econometric Society and Economic Theory Fellow. Honorary Professor, University of Technology, Sydney, UTS. Has published in Econometrica, American Economic Review, Journal of Economic Theory, and many other journals. I won't take more time. Works principally in the areas of microeconomic theory, game theory, industrial organization, experimental economics, etc. And his most important paper, very famous paper, Minimax Play at Wimbledon. So I will spend no more time. We've already used up some time. So we now have Professor Wooders for the first plenary session. Professor Wooders.
Thank you. Okay. Okay, great. Thank you. Good morning. It's a pleasure to be here. It's my first trip to India, so it's exciting. I still have a mic, right? Yes, I think so. Okay, great. So today I'm going to talk about testing game theory. And in fact, it's a little bit more narrow than that. It's really about testing the theory of mixed strategy Nash equilibrium. But let me get started. So first of all, before I start though, I'm going to talk about work, some of my own work by other people, but I've been very fortunate over my career to have wonderful co-authors. And on the work that I'll talk about today, some of my co-authors are, for example, Mark Walker. Mark is a co-author in the first work I did on tennis. He was at the University of Arizona when I was an assistant professor, hired there. Jason Shackett was a graduate student at Arizona. Rabah Amir was my colleague at Arizona. He's now at Iowa. Matt Van Essen was my PhD student at Arizona. He's now at University of Tennessee. Roman Goriat was a postdoc at NYU Abu Dhabi. He's now at Deakin University. And Lionel Page is at University of Queensland. Okay, so with that out of the way, let me go on. So in many strategic situations, it's important that one's actions not be predictable to one's opponents. In fact, the origins of game theory lie in an attempt to understand such situations. So this goes all the way back to von Neumann's min-max theorem in 1929, and Nash's notion of an equilibrium in mixed strategies, or of equilibrium, that was in his 1950 paper. Okay, so I'm going to talk about Nash equilibrium and min-max. And in the context that I'm looking at today, which is going to be two-player zero-sum games, those things are entirely synonymous. So whenever I say min-max, you can think mixed strategy Nash equilibrium. Okay. So today I'm going to discuss testing game theory and I'm going to talk about data both from the laboratory, from laboratory experiments, and from the field. I'm going to talk about mixed strategy play. And what I want to do in today's talk is I want to emphasize the interaction of theory and data. Okay, and where by data, I'm going to talk about both experimental data, but I'm also going to talk about field data. In fact, mostly of what I'll talk about is field data. So, of course, what's the connection between theory and experiments? Well, of course, economic theory, when you see a model that, one might be interested in the empirical relevance of that model, one doesn't have to be interested, but if one is interested, okay, then one means of learning about that is to run experiments, okay, laboratory experiments. Okay, so experiments allow us to test the empirical content of theory in a controlled environment, right? If we're running an auction experiment, for example, the experimenter controls the distribution, or can control the distribution of the bidder's values. Also, by manipulating parameters in the environment, one can establish causality, right? So if you want to understand the effect of reserve prices on seller revenue, you can vary the reserve price in an experimental setting. Okay. But also, once you start thinking about experiments, you discover that experiments themselves raise new theoretical questions. Okay, and so I'm going to talk about some examples of that today. Okay, so I'm going to start by going back to 1987, which is a classic experiment on mixed strategy play by Barry O'Neill. Okay, this was a paper that was published in the Proceedings of the National Academy of Sciences. Okay, so let me tell you about O'Neill's experiment. So O'Neill had the subjects play a card game. Okay, so in this game there were two players. They simultaneously chose cards: ace, deuce, trey, or joker. And the rules of the game, let's see, is this a pointer? Yes. The rules of the game were that the row player wins if they choose different number cards, or non-joker cards. Row also wins if they both choose the joker card, right? And so this matrix here illustrates the payoffs for O'Neill's game, right? So we see that the row player wins if they both choose joker, and the row player wins if they both choose number cards, but they are different. Otherwise, the column player wins. Okay, so that's the rules of O'Neill's game. Now, it's easy to work out the mixed strategy Nash equilibrium of this game. There's a unique equilibrium. It's in mixed strategies. And in fact, in equilibrium, each of the players play each of the number cards with probability 0.2, and they play the joker card with probability 0.4. Okay, so for example, we can see that if the column player follows this mixture at the bottom, okay, then the row player wins. If the row player chooses 1, the row player wins if 2 or 3 are played. That happens with probability 0.4. The row player wins by playing 2. The row player wins if 1 or 3 are played, which also happens with probability 0.4. If he plays a 3, he wins if a 1 or a 2 is played, which happens with probability 0.4. And finally, if the joker card is played, then the row player wins if the other player plays if column plays the joker card, which happens with probability 0.4 as well. Okay, so the point is that given the column player's mixture, any pure strategy by the row player is optimal. It gives him a payoff of 0.4. And that means that any mixed strategy by the row player is a best response to the columns player's mixture. Okay, and it's easy to verify that the converse is also true. If the row player follows the same mixture, okay, then the mixture at the bottom is actually a best response for the column player as well. So this is a mixed strategy Nash equilibrium. Okay, okay. So what did O'Neill do in his experiment? O'Neill had 25 pairs of subjects come into the lab, and they played this game. They played this game for 105 rounds. Okay? And the stakes were not big. The stakes were 5 cents a hen. Okay? So, and in fact, and that's the way I've written the payoffs here. Notice that I've written the payoffs now in terms of if they both play joker, then the row player wins the row player wins 5 cents. Okay. So why did I write things this way? Well, that's the actual game that O'Neill had the subjects play for money, not utility. Those payoffs are money payoffs in terms of cents. Okay, but a nice feature of this game is that it has only 2 outcomes. The row player either wins 5 cents or the row player loses 5 cents. And why is that important? That's important because it means that there's no issue about the row player's risk attitudes. Okay, so long as the row player prefers to win 5 cents than to lose 5 cents, then we can assign a utility of 1 to the outcome where he wins 5 cents, and a utility of 0 to the outcome where he loses 5 cents. Okay, and that represents the game when we transform it into utilities instead of money. Okay, so that was an innovation of O'Neill's experiment, which was to run an experiment which had only 2 outcomes, and therefore there was no issue about risk attitudes. Okay, so he didn't have to, when he was testing the theory, when he was testing mixed strategy Nash equilibrium, he didn't have to make any assumption. He didn't have to assume, for example, that the players were risk neutral. Okay. Okay. Which is good, right? If we want to test a theory, we'd like to do it with as few auxiliary assumptions as possible. Okay, so as I've said, the nice features of this game are that the equilibrium doesn't depend on the player's risk attitudes. It has a unique Nash equilibrium, which is asymmetric. Okay, and the equilibrium is not obvious. Okay, at least it's not obvious to me. Most people I've asked don't feel that this is obvious. And actually, the question of whether or not this equilibrium is obvious is going to come back. We'll come back to that question when I talk about in the lecture I give this afternoon. Okay. Okay. So this is O'Neill's data. Okay, and what this data shows, or what this table shows, is it shows the joint frequencies over the players' action profiles. So this 0.44 here, for example, 0.044. That shows the frequency that both the players played the one card. Okay, and in red is actually the theory, right? The theory says both the players should play the red card with probability. That should happen. That should be the outcome with probability 0.04. Okay, so if we look at the data, we can look at the if we sum across these columns, we can see the probability that the row player chooses the one card. That's actually 0.22. The theory is 0.2, right? For the 2 card, it's 0.215. The theory is still 0.2, 0.203, the theory. And then the joker card for the role player is 0.362, which is a little bit less than the theoretical prediction. Okay, so the theory looks pretty good, doesn't it? I mean, in the sense that, like, again, it's not obvious, at least to me, what the equilibrium is of this game. And it certainly doesn't seem obvious to the subjects. Okay, they came in and they behaved in a way that it doesn't exactly match the theory, but it seems to be in the right ballpark, right? We in fact see that the column player, pardon me, the row player, is playing the number cards at similar frequencies, and he's playing those number cards at roughly half the frequency of the joker card. So when O'Neill, this is before my time, but I'm told that when O'Neill presented these results, people were very excited. Because this was the first test, in some sense, where mixed strategy Nash equilibrium kind of worked. Okay, and in some sense, it has worked. It's pretty good. Okay, and by the way, I've talked about the row player, but we can see that the situation for the column player is very similar, right? Again, the column players, it's not matching. We don't exactly match. The empirical frequencies don't exactly match the theoretical frequencies, but we don't expect them to exactly match because this is a mixed strategy equilibrium, right? The players randomize. Okay, so very nice, very nice, surprising results. But of course, when you have such things, then somebody's going to come and rain on your parade, and that's what Brown and Rosenthal did in 1990. Okay, so they have an econometric paper where they basically looked more carefully at O'Neill's data. Okay, and what they said is that, well, okay, the data looks pretty good in aggregate, right? That table I just showed you looks good. But we can actually test. The theory doesn't just make a prediction about aggregate play. It makes a prediction about individuals play. Okay? It says, for example, that that a player plays each of his cards, each of the number cards with probability 0.2, and the joker card with probability 0.4. And we can test that. We can do simple statistics to test whether each player is actually following their equilibrium mixture. Okay? Brown and Rosenthal test that. And they find that at the 5% significance level, there are 15 of the 50 subjects. There are 15 of the 50 subjects for whom we can reject the null hypothesis that they're choosing cards according to the equilibrium mixture. Okay? When we have 50 subjects at the 5% level, we expect 2.5 rejections. So 15 is way too many. Okay? We shouldn't get so many rejections. Okay, if we look, we could of course just focus on the joker card. We could look at a player's decision to play the joker card versus playing a number card, right? That's a binary decision, joker or non-joker. Okay, and we can test whether players choose the joker card with probability 0.4, and that's rejected for 17 of the 50 players. Again, the null hypothesis is rejected at a much higher rate than expected. Okay, another problem with the data, which you couldn't actually see in the chart, in the table that I just showed you, is that it turns out that the players' choices were serially correlated. Okay, so the theory says that you should actually play, each play should be independent of everything that happened in the past. But you can reject that. Okay, so you can reject serial independence for 15 of the 50 subjects. In most cases, in 13 of the 50 cases, you reject because the players are switching the card too often. Okay, so, and this is actually consistent with a lot of prior experimental evidence that people are just not very good at generating random sequences. Okay, okay. So let me just show you a little bit, give you a sense. I want to show you this picture to give you a sense of why of how the theory is being rejected by Brown and Rosenthal. So remember, O'Neill had his subjects play 105 hands. So if they're playing the joker card with probability 0.4, then after 105 hands, they should play, the expected number of joker cards is 42. Okay? And what I'm doing here is I'm looking on the horizontal axis, I'm looking at the number of joker cards played after 105 hands. Okay, the red bar here is at a maximum if I look at the bin between 41 and 43. So 41, 42, or 43. the theory, mixed strategy Nash equilibrium, says that like 23% of the players should choose either 41, 42, or 43 joker cards after 105 plays. Okay, so the theory makes a prediction about the distribution of the number of joker cards after 105 plays, right? And that distribution is shown in red. Okay, so what do we have in blue? In blue, we actually have the data. Okay, and what we see is that there's too much heterogeneity in the play of joker cards, in the frequency of joker cards. We have, for example, in O'Neill's data, there are 2 subjects who played either 17, 18, or 19 joker cards after 105 plays. So these guys, we would reject that they're choosing the joker card with probability 0.4. They're playing joker 2 infrequently. We reject for these guys as well. So we have 10 subjects for whom we reject the theory because they're playing the joker card too infrequently. And we have 7 more subjects for whom we reject the theory because they're playing the joker card too frequently. Okay? So I'm going to show you again later on in the second lecture. I'll show you another picture that looks like that. We'll see this picture, this exact same picture, later this afternoon. Okay, so what we see then with O'Neill's data is there's actually too much heterogeneity in how the players play the joker card to be consistent with mixed strategy Nash equilibrium. Now, I want to actually come back and let's put experiments aside for a moment and let's think about game theory. Because I said something earlier that you might actually want to question, right? So we know that when we have two outcomes, we don't have to worry about risk attitudes. We assign a utility of 1 to the better outcome and a utility of 0 to the worst outcome. Okay, but when you think about O'Neill's experiment, O'Neill didn't have the subjects play the game once. O'Neill had the subjects play the game 105 times. So we know, in fact, that O'Neill's experiment, like many others, is really, he has the subjects play a repeated game. And the repeated game has more than 2 outcomes. Okay, let's imagine that we repeat the game twice. If we repeat the game twice, I can win twice. I can win then lose. I can lose then win. Or I could lose twice. So now we have 4 outcomes. And so now it's not so obvious, perhaps, that O'Neill's experiment really does control for risk attitudes. And in fact, this question was raised. I won't tell you who wrote this, but they said, we believe that it's a mistake for O'Neill to use an experimental design featuring repeated play against the same opponent. Aside from reputational problems, the super game that results does not have only lose or win outcomes and hence negates the attempt to control for risk attitudes. Okay? Okay, so this is actually a game theory question that's raised by thinking about an experiment. Okay? This is not an experiment that's motivated by theory. This is a theory question. So the theory question is this statement correct, right? That I've quoted here. Okay, and the answer is actually that statement is not correct. Okay, O'Neill's experiment does control for risk attitudes. Okay, and what a paper of mine shows that if the stage game has 2 outcomes, the stage game is strictly competitive, and it has a unique Nash equilibrium, then the unique Nash equilibrium of the super game, of the repeated game, calls for Nash play at each stage, provided that the player's preferences over super game outcomes satisfy a weak monotonicity condition. So what is the monotonicity condition? In a twice repeated game, the monotonicity condition is just that we need that the players have to have preferences where winning twice is preferred to either winning then losing or losing then winning, and both of those outcomes are preferred to losing twice. Okay? It doesn't require, the monotonicity condition does not require that a player be indifferent to the order in which he wins or loses. Okay? It doesn't require that a player be indifferent between winning and losing versus the lottery where he wins with probability half, he wins twice with probability half, or loses twice with probability half. Okay, so in fact, O'Neill's experiment does control for risk attitudes. Okay. Okay, this means, for example, an implication of this result is that one can, for example, vary stakes across the stage games, and that wouldn't affect the equilibrium play. So we could have them play the first game for a nickel. We could double the stakes in the second game. They'd play for a dime. We could double them again for the third game, and so on. And equilibrium would still be the same, which is that at every play, they should still play the number cards with probability 0.2 each and the joker card with probability 0.4. Okay. Okay, so theoretical aside, let's come back and talk about experiments some more. Okay, so there have been many experiments, O'Neill's, which we've talked about, and others, that have tested the min-max hypothesis, or mixed strategy Nash equilibrium, and the theory hasn't done very well. Okay? Why hasn't it done well? Well, okay, what are the possibilities? One is that students, the typical subjects, student subjects, are inexperienced. They don't have much experience with playing games, strategic games. Another explanation is that, well, maybe the financial stakes are small. Okay, they're playing for a nickel a hand. Maybe that's not enough. Okay. Also, a laboratory experiment typically takes place over an hour. There's just not much. I mean, how can you learn how to play an equilibrium in an hour? Okay, in a mixed strategy game. Okay, there's limited scope. There's opportunities to learn are very limited. So the question that motivated Mark Walker and I when we started this research program was, well, can we find anywhere at all where the theory works? Okay. Okay, so Mark Walker is a tennis player. I'm actually not a tennis player. Yeah, sorry.
One quick question. In the experiment, are the row and column players remain the same across different stages? Or?
Yes. So in O'Neill's experiment, in O'Neill's experiment, you and I would sit down and we would play the game against each other, fixed pairs for 105 rounds, and then we'd walk out. We'd get paid and we'd walk out. Okay. Okay. So sports. In sports, it's important to be unpredictable, right? So in baseball, the pitcher won't do well if the batter can anticipate the type of pitch that he's going to get. And actually, we can see that because in the 2017 baseball season, the Houston Astros actually were stealing signs. So the Houston Astros, the batters, knew what kind of pitch they could anticipate the pitch they were going to receive. Okay. Okay. In soccer, a player making a penalty kick is unlikely to be successful if the goalie knows whether the kick will be to the left or to the right. In tennis, the server is not going to do well if the receiver can anticipate the direction of the serve. In poker, a player needs to randomize in order to conceal his hand. So poker is not exactly a sport, but it's like a virtual sport, perhaps. Okay, so the problem with using data from the field, though, is that it's very hard to identify what are the testable implications of the theory, right? So think of poker, for example. Poker, if you think about two-player, heads-up, Texas Hold'em, okay, in a ring game, not a tournament, it's a simple game. It's been solved, in some sense, that game has been solved by, numerically, by computers, right? A computer can play two-player poker optimally, okay, but we don't know what the equilibrium looks like. Even for poker, we don't know what it looks like, okay? We don't have an analytic solution to poker. Okay, so where in the real world can we find data that actually allows us to test theory, okay? And so let's think about, I want to talk about tennis, okay, as a way to test the theory. So let me actually show you a little bit of tennis. Now I'm a little concerned about the sound here. It's not going to blast, right? No. So, okay, we'll see. Okay, hold on to your seats here. Okay, now there's no sound at all, so that's... Let me try. It would be nice to have some sound. Okay, we're working on the sound. Okay, let me back this up to the beginning. Okay, so let me just...
Lit.
So this is Wimbledon 2008. Roger Federer is serving right now. It's the first point in the game, which means that Federer is actually standing over on this side of the court, which is called the deuce court. Okay, Federer has to serve the ball. Some of you may not know a lot of tennis, so I'll explain a little bit. I'll explain a little bit. So Federer serves the ball. The ball has to cross the net. It has to land in this little white rectangle over here. Okay. Okay. So let's look at some data. So, and let me wrap this back to the beginning. Okay, that's a let. That means that when he served, the ball actually touched the top of the net, and so that's like a do-over, okay? And so he's going to do it over.
It's not a bad first point.
Whoops. Okay, so Federer served. He ultimately won the point. So, and that shows the score here, right? So 15 to so Nadal won the point. Okay, thank you. Nadal won the point. And I'm trying to get the video back to the right spot. Okay.
He's expecting to win a lot of points off that first serve.
So second point.
Let first service.
Fall.
Federer has been absolutely phenomenal off serve. I mean, look at that.
Okay, so Federer served from the deuce court, the first point, from the ad court, the second point. Now he goes back to the deuce court for the third point. Okay, and by the way, pay attention if you can to where Federer is serving the ball. Okay, might be hard to see.
That is scary. Even Sampras would be impressed. As great a serve and volley as he was. He threw in more doubles. He took more chances on his second serve.
Federer's been broken only twice in his 6 matches here.
And you notice he's not going to be hurt as much with this shot. I mean, that's low in his hitting zone. He likes that. But Nadal's going to have a tougher time getting it up above his shoulders on this.
Okay. So let me go back to the slides. Okay, there we are. Thank you. Okay, so that's this is an example of a match that's actually in the data set that I'm going to talk about. So let's just look at that data from what we saw there. So this was remember, Federer started serving from the deuce court. This was his first serve. It was to the right. It was basically, if we think about dividing the court, we can see that this ball was served to Nadal's right. Okay, whereas this serve up here, the 10th serve, that was served to Nadal's left. Okay, so the first serve was a let. It was to Nadal's right. The second serve, still from the deuce court, was to Nadal's right. Okay, the third, fourth, fifth, and sixth serves were all from the ad court. Okay, so third, fourth, fifth, and sixth. So the third was a let. I think the fourth was a let. There was a fault. And then this serve actually is in some sense kind of to the center of where Nadal was standing. Okay, but generally, aside from serve 6, the serves were essentially to Nadal's left or right. Okay, and then if we put it all, this actually shows not just those serves. This shows all the serves that Federer made from the deuce court in the first serve. Okay, and all of these blue points here correspond to the actual bounce point of the serve. Okay, it tells us where the ball actually landed in the court. Okay, the data is recorded by a computerized ball tracking system called Hawkeye that uses a system of cameras to measure the location of the ball and the bounce point very precisely. Okay, and we can see when we look at the data, we can see that these are serves. The serves are concentrated around serves to the receiver's right or serves to the receiver's left. And of course, at some point they switch over to the other side of the net. So again, here this dashed line is an imaginary line that we use to divide the left side from the right side. Okay, and again, we still see that the serves are concentrated to the receiver's left or the receiver's right. Now, there's one more thing about this picture that you might not have, that you probably noticed, which is that there are these red points here, right? There are these red dots. Okay, those red points are actually imputed bounce points. So the way Hawkeye works is that it records the position of the ball using 3 polynomials for the x, y, and z location of the ball in space as a function of time. So what those red points represent is that when the server, in some serves, the net intervenes, right? The net blocks the ball, okay? And what we can do is we can take those polynomials that you describe the position of the ball as a function of time, and we can run time forward, and we can see where the ball would have landed had the net not intervened. Okay, so these are points where we don't actually observe the bounce point. The red points, we don't actually observe the bounce point, but we can impute the bounce point given the data we have about the location of the ball. Okay, and so the point is that in the serve in tennis, the server is essentially making a binary decision. The server is deciding to serve either to the receiver's extreme left or the receiver's extreme right. Okay. Another key feature of tennis is that the points have binary outcomes. Every point served, you either win the point or you lose the point. Okay? So there's no draw, for example. Okay? And also, it's a feature of tennis that in a tennis match, you either win the point or you lose the point, right? So it's a binary outcome, just like the O'Neill game. Okay, so, all right, let's continue. I'm going to talk about tennis, but the ideas I'm going to talk about are essentially the same for soccer. Okay, this is a collection of around 17,000 penalty kicks in soccer. Okay, and it shows the position of the ball as it passes through or past the goal. Okay, and what we can see in this picture is that in red we have these are misses, right? Those are kicks that just went outside the goal. Okay, in black we have shots that they actually hit the post. Okay, they hit the crossbar or one of the posts. In blue we have the saves. So those are balls where it would have been a goal, except that the goalie blocked it. Okay, and then in green we have the goals. Okay, so you can see that again, kicks in penalty kicks are also tend to be concentrated to the left or to the right. Okay, let me follow that up a little further. This is a picture that shows the distance in meters to the nearest post. Okay, and again, we see that if the distance between the posts is I think 24 feet or 8 meters roughly. Okay, so if at zero distance to the post we actually have it hits the post. Okay, to the left we have it's actually outside the goal. Okay, that's a miss. Okay, and then here this histogram this empirical density shows the distribution of the location of the kick. okay, of the shot. Okay, and we can see that, in fact, the vast majority, it's not clear from the prior slide, but one can see that the vast majority of the kicks, penalty kicks, are close to the post. They're not if they were at the center, if they were concentrated around the center, we'd see a bunch of mass over here, which we don't see. Okay. Okay, so I'm going to talk about tennis, but the ideas for tennis, the same ideas that I'll talk about apply to soccer. Okay, so what do we know about professional tennis or professional sports, right? So when in professional sports we have players who are experienced and well motivated, and we know there that the data is actually the behavior conforms more closely to the theory. So the first paper on this was my paper with Mark Walker. Okay, there was a follow-up paper that looked at some different data by Hu, Huang, and Tang. Chiapori, Levitt, and Gross-Close looked at, this is a paper about soccer, and Plashes Huerta 2003 is also a paper about soccer. Okay, there are some advantages and disadvantages to looking at soccer versus tennis. So for example, in soccer, you observe the actions of both the kicker and the goalie, right? Whereas in tennis, we don't really observe the action of the receiver. We certainly observe what the server does, but we don't observe the action of the receiver, okay? And so that's would seem to be an advantage for soccer. Now, soccer also has a significant disadvantage, which is that typically a given kicker and a given goalie encounter each other very rarely. Okay, so you have basically you don't have a repeated interaction in soccer the same way you do in tennis, right? In O'Neill's experiment, he had a pair of subjects. They come in, that pair came in and sat down. They played 105 rounds against each other. That actually looks a lot like a tennis match, right? In a tennis match, you have the same server and receiver who play a whole match, okay? So in that respect, it's not clear that that difference means that it's not clear to me that it's not totally clear that soccer is actually a good way of testing mixed strategy play. Okay, but so we have these results about from professional sports about soccer and tennis. Now, a critique of these papers could be that they have low power, right? So, those papers, my paper with Mark, for example, we don't reject the theory, right? We cannot reject the hypothesis. I'll come to those in a minute. We can't reject the theory based on the data from Wimbledon. But it's also the case that Walker and Wooders looked at only 10 tennis matches. Okay, we looked at championship matches, we looked at long matches because we wanted to get more data, but we only had 10. Okay, why did we only have 10? We only had 10 because we actually had to watch the video to get the data for this talk, okay, or for that paper. Okay, and it takes time to watch video. It's actually hard to get the video. So so Walker Wooders had 10 matches and only just over 3,000 serves in the data set. The data from soccer there's less data when it comes to penalty kicks because like Chiapori, Levitt, and Gross-Close, they only had 459 penalty kicks. Plashes Huerta had just over 1,400 penalty kicks in his data. Okay, all of this data is only about men. Okay, with the exception of Hu, Hung, and Tang, which had data for 9 women's matches. Okay, so again, if you test the theory and you fail to reject, well, it could be that the theory is true, but it also could be that you just don't have much data. Your data doesn't have, and therefore you don't have much power to reject the theory. Okay, so what I'm going to talk about next is a paper that is with Roman Goret and Lionel Page, and it is, I think, provides the strongest evidence that the behavior of sports professionals conforms, at least in one dimension, to theory. And there are really 2 contributions to the paper. One is that we have more data, right? So why is this? Why do we have something new to say here? Well, we have more data. We have a lot more data. Okay. The second thing is that we actually had to develop a new statistical test to actually execute this paper. I'll say more about that in a bit. Okay. And what we're going to find, I'm going to show you that the theory works quite well. Okay. But I'm going to show you the theory doesn't work. There's a difference between the degree in which the theory play conforms to theory in men and women's tennis. Okay, and I think the last bullet point, which is very interesting to me, is that when the theory performs poorly, we're going to see that actually better players, the better tennis players, behave in a way that conforms more closely to theory. Okay, so all of the players in our data set are elite players, right? They're professional players, and yet the players who, among the very best of those players behave in a way that conforms more closely to theory than the players who are also extremely good, but not as good. Okay. Okay, so let me talk about theory. And this is going to be simple theory, right? So how do we model tennis? How do we model a serve in tennis? Okay, or how do we model a kick, a penalty kick in soccer? Okay, and we're gonna model each point in tennis as just as a 2x2 normal form game, right? So we have this is the 2x2 game. The server chooses left or right, and the receiver chooses to overplay left or overplay right. In other words, prepare for something to the left or prepare for a serve to the right. Okay, again, we don't actually observe the receiver's actions in tennis. Okay, but for any given pair of actions, there is some probability that the server wins the point. So pi LL is the probability that the server wins the point when the server serves to the left and the receiver anticipates a serve to the left, okay, or overplays left. Okay, so of course in tennis, one player or the other wins the point. So if these are the probabilities that the server wins, then 1 minus these probabilities is the probability the receiver wins. Okay, so what assumptions do we make about these payoffs? By the way, so when we look at the data, we're going to focus on the direction of the serve. Does the server serve to the left or to the right? And we're going to look at, does the server ultimately win the point or not? So a lot of stuff happens between when the server serves and when the point is finished, and we don't care about anything of that. The theory doesn't actually tell us, to my knowledge, anything about what happens in between. Okay, but the theory says that, I'll say more about the theory now, but we're focusing in a moment, but we're focusing on, again, the serve direction and the final outcome. Okay, so what are the assumptions we make about these probability payoffs? First of all, we assume that these probability payoffs are such that the equilibrium is in mixed strategies. Okay, and if you actually look at data from tennis, we actually don't see there's no match in our data set where people just serve where somebody serves to the same direction all the time. That just doesn't happen. Okay, the second assumption is that there are going to be 8 distinct point games. So we have, if I want to describe a tennis match, I'm going to need not just one of these matrices, I'm going to need 8 of them, right? So why 8? Well, first of all, those probability payoffs, those probabilities of winning the point, they're going to depend upon who's serving. It's going to be different for Federer. There will be different numbers for Federer than they are for Nadal. Okay? It'll depend upon whether the point is served from the ad court or the deuce court, right? A player is standing, when he serves, he can be standing in two different positions in the court, the ad court or the deuce court. Okay, and potentially where the player stands in the court might affect his probability of winning the point. It might affect these probability payoffs. We don't know, but it could. And so we're allowing these probability payoffs to depend upon, the court from which the ball is served. And finally, those probability payoffs will depend upon whether the serve is a first serve or a second serve, right? So in tennis, if the first serve is, you can either win on your first serve, you can win, okay? But on the first serve, you can also fault. In other words, when you serve, the ball goes outside of the court, okay? If you fault, then you get a second serve, okay? But your probability of winning the point after you fault is going to be lower, because if you fault again, if you have a double fault, then you actually lose the point, okay? So these probability payoffs will depend upon whether it's a first serve or a second serve. Okay, so we have 2 different servers, we have 2 different courts, we have first serves and second serves, so 2 by 2 by 2. That means that to describe a match, we need 8 different point games. Now notice that this is in some sense a simple model, right? So we're not accounting for the fact this model doesn't have effort as a variable in it. Okay, there's no notion of, say, a player having a store of energy. So this model, like all models, is a simplification. Okay, and we might end up rejecting the theory simply because maybe that's an important feature of the game that we've neglected. But the data will tell us that. Okay, so what are the testable implications of the theory? Remember, that's the challenge. when we run a laboratory experiment, as O'Neill did, we control the payoffs. We know what the payoffs are, assuming that we don't need to make assumptions about risk attitudes or things like that. In a laboratory experiment, we know the payoffs, we can calculate the equilibrium, and we know, and that forms a basis for prediction. With data from the field, the question is what does the theory predict when we don't actually know those probability payoffs, and we don't. Okay, so the first prediction of the theory is that the probability that the server wins the point when he serves to the left is the same as the probability he wins the point when he serves to the right. Okay, so this is just a simple consequence of mixed strategy Nash equilibrium. In a mixed strategy Nash equilibrium, it has the feature that all actions in the support of your equilibrium mixture give you the same payoff. Okay, and your payoff here is just whether or not you win the point. Okay, so the theory says in a mixed strategy Nash equilibrium, each player's probability of winning the point in point game I is going to be the same for serves left and serves right. Now, so if I look at so this is the prediction for point game I for first serves from in the Federer versus Nadal match for first serves from the deuce court. Okay, when Federer is serving, in all of those instances, the probability that Federer wins when he serves to the left should be the same as the probability he wins when he serves to the right. Okay, of course, those probabilities differ across point games. Those on the second serve, those probabilities will be different from the first serve. But again, even on the second serve, the probability of winning on the left, when you serve left, should be the same as the probability of winning when you serve right. Okay. All right. How are we doing for time? Did I start? I started at 9:30, right? So, okay, cool. Okay. The other prediction. Okay, the second prediction that comes from the theory is that the direction of the serve should be serially independent. Okay, so for each point game I, we observe a sequence of serves, right? Say first serves, and we can write them down in the order in which they occurred. And the hypothesis is that the sequence of directions of serves is serially independent. Now, that actually raises a new theory question, right? Because the simple theory that I showed you was for a one-shot game. But in tennis, they don't just play one point. In tennis, they play a whole match. And a match is a complicated, extensive form game, right? So in a tennis match, you have to win points to win games. You have to win games to win sets. And then you have to win sets to win the match. So there's a question, what is equilibrium in a tennis match? And the answer to that question is actually solved by a paper with Mark Walker and Rob Amir. It studies a class of extensive form games called binary Markov games that we call binary Markov games. Okay, and it shows that in fact it's in the equilibrium of the tennis match. Okay, the equilibrium of the tennis match has the feature that you play for every point. You play the Nash equilibrium of the game for a point. Okay, so but again, this theory question is arising out of how to understand or how to think about some field data, right? And it motivated that paper was in Games in Economic Behavior in 2011. It motivated a completely new paper. Okay, again, remember this is an important question because in tennis, the players actually don't win. They don't play to win points, right? They don't care about the number. They want to win the match. Okay, they're not winning points is just a means to an end of winning the match. Yes.
Does any of these results will also depend on how long the rally goes between the players?
No, that's not even. We don't. The theory just says. So the question, the question was, does any of this depend upon the length of the rally, right? What happens between the serve and the final outcome? And the answer is the theory that the testable implications the theory we test doesn't have anything to say about the length of the rally, right? So I'm serving. I have to decide whether to serve left or serve right, and I'm playing an equilibrium where I'm mixing, okay? And at the time I serve, I have some expectation of what's going to happen if I serve to the right and what will happen if I serve to the left. And in a mixed strategy Nash equilibrium, I'm going to take account of all the different things that might happen if I serve to the right. I might fall, there might be a long rally. I might win immediately on an ace. Okay, but the point is that at the time I make that first decision, I should be indifferent between serving left and serving right. My probability of winning the point should be the same when I serve left or serve right.
Like, is there any possibility of anticipation, like the rally goes, like yo is part of that?
It doesn't, once, the problem is that, the theory doesn't, as far as I can tell, as far as we know, the theory doesn't say anything about what happens after the serve in terms of the rally, right? In some sense, every rally is different, right? It's going to depend upon, where the ball bounced, how well the receiver returned the ball, and so on. So we're just saying, at the moment you make a decision, think about poker, right? I have a hand. I have to decide whether I'm going to call, say raise or raise, call, or fold. Right? Now, whatever I do, a bunch of different things might happen in the end, right? So if I'm thinking about, if I'm mixing between raising or calling, I have to make a forecast about the outcome in either case. If I'm indifferent, if I'm randomizing, then my expected winning should be the same, okay? And from those two actions, although many different things may happen after I call versus after I raise. So we're assuming that the players take account of all of this stuff when they're making that calculation, which is, again, that requires some sophistication. It's not always, so part of what we're testing is whether players actually can do that. Okay, so let me talk about the data. The data is the official Hawkeye data from between March 2005 and 2009. Okay, we have data for both men and women, first serves, second serves. For male first serves, we have almost 250,000 serves in the data set. Okay, so this is why it's great to have computerized data versus, say, watching videotape with a beer in hand. Okay, it takes a long time. Computerized data is much easier. Okay, so the data it's played on a variety of different surfaces. In women actually play matches that are the best of 3 sets, then play best of 5. So there's a difference in men's matches. Tennis matches tend to be longer than women's matches. Okay, different events. So for men, we have a total of 1,995 matches in our data set. Okay, this is a picture of our data. So this is I showed you Federer serves from the video from the first set with Nadal. Okay. These are all the ball bounces for serves from the deuce court by men. And again, there's data on both sides of this picture because at some point the server walks across, he switches to the other side of the net, and he serves that way. Okay? So, and again, the blue shows all the observed bounce points, and in red we have all the imputed bounce points, and these dashed lines are, again, these dashed lines don't actually appear on the tennis court, okay, but they are how we distinguish between serves to the left and serves to the right. Okay, and you can see that there are some serves that are near the center, but there are not many serves. Okay, and here's what we're going to test. We're going to test the null hypothesis that the probability of winning when you serve to the left is the same as the probability of winning when you serve to the right. And the theory says that this should be true for every match in our data set, right? So that's what we mean by for all I. Okay, so here's like a bit of an interesting aside. So of course we had this big new data set. And what's the first thing you do when you have a new data set? Well, you take the data set and you use the same tests that have been used in the prior literature, and you see whether you get what kind of results you get. Okay, so the first thing we did is we just ran Walker and Witters have a statistical approach for like testing the theory, and we just adopted the Walker-Witters approach, and we saw what we got. Okay, but we applied the Walker-Witters test to the Hawkeye data, and we reject the null. Okay, and that's okay. That was a bit surprising. It's disconcerting even. Okay, and so what's going on? So, well, okay, there are two possibilities here. Maybe at least two possibilities, right? So we have a bigger data set. We use the same statistics as Walker-Wooders, but we get a different answer because Walker-Wooders did not reject the theory, did not come close. But now we do reject the theory when we use the Walker-Wooders statistical approach. First possibility, the theory is false. And we're just discovering that because we have a bigger data set, right? Okay. The second possibility is that somehow the statistics from Walker-Wooders aren't actually valid in the context where we're using them, okay? And how do you answer that? Well, okay, so what we did is we ran Monte Carlo simulations. We simulated the data, and with Monte Carlo simulations, we can simulate the data under the assumption that the null is true, right? So we know the null is true, okay? And we simulate the data, then we apply the Walker-Wooders methodology to it, and we see what the Walker-Wooders tests produce, okay? And it turns out that actually when we use a bigger data set, when we use a data set that has 250,000 serves, the Walker-Wooders tends to reject the null hypothesis even when the null hypothesis is true, okay? So, okay, I'll say maybe, I'm not sure how much more time I'll have to talk about that in this talk. Walker-Wooders, what they did was fine, but it's fine. It's fine when you have 10 matches. It's not fine when you have thousands of matches. Okay, then there are asymptotic assumptions underlying the statistical approach that lead to a rejection of the theory, even if the theory is true. Okay, so what we had to do is we had to come up with a new. So yeah, we simulated data for 3,100 matches. And when we simulate the data, knowing that the null is true, we reject the null. Okay, so what we need to do is we actually need to develop a new statistical test, or else we don't have a paper, right? If we can't, I mean, that was what we were looking at. Okay, so it turned out that we could actually solve this problem. We could find a statistical test that actually had the properties that we needed. Okay, so let me work towards that. But let me tell you first. Let's go back and just think about what the data is for a point game. So the data for a point game is really simple. It can be measured by 4 numbers, right? If I have so in a point game, I observe the number of serves to the left that are successful. So there's a win. I observe the number of serves to the right that are successful. I also observe the serves to the left that are failures or losses, and serves to the right. So I can describe the outcome of a point game by 4 numbers. Okay, so the question is, why does the test work for a small number of games but not a large number? And the answer is that the test that Walker-Wooders use assumes that I'll talk about it in more detail in a moment, but it looks at the distribution of the p-values that come from every point game. We have a test, and we get a p-value associated with that test. Okay. So when Walker-Wooders, in the approach that Walker-Wooders use, that relies on the asymptotic, to obtain that p-value, we rely on the asymptotic distribution of the test statistic. Okay? And when you have a data set that's not too big, then that's not a problem, right? So we can do Monte Carlo simulations using the Walker-Wooders approach for sample sizes that are the size of Walker-Wooders, and we reject you reject the true null at the 5% level 5% of the time. Okay, but the problem is that when you have hundreds of, or not, well, I guess we have, when you have thousands of point games, then every one of those point games you're getting the p-value a little bit wrong because it's relying on an asymptotic distribution. Okay. And when you have thousands of p-values, the test, the Kolmogorov-Smirnov test, actually picks up that those p-values are not uniformly distributed, even under the null. Okay, as they should be. So what we do is we develop a test, which I'll describe in a moment. We develop a test where we don't have to make any asymptotic assumptions in order to obtain the p-values. That's the key thing. So the p-values that we get require nothing about asymptotics. Okay? So yeah, we discussed this at more length in the paper, but that's the rough idea. Okay, so let me tell you about what we do. So, okay, So we're interested in two hypotheses, right? So I have to remember to talk this way. So we're interested in two hypotheses. The first is just that in every individual point game, the probability of winning when you serve left and serve right are the same. The second is what we're really interested in is that the probability of winning when you serve left and right, it's the same, and that's true for all point games, right? That's what it means for the theory to be true, right? It has to be true for all the point games. Okay, so let me start by describing what's called the Fisher exact test. Okay, so as a kind of a foundation, we're using the Fisher exact test to test the null hypothesis that the probability of winning when you serve left and right is the same. Now, this is kind of an amazing test, actually. I'm a theorist, I'm not a statistician, but I think this is pretty cool. So let's call it, we have this, we have a density F. F is a function of the number of winning serves to the left, conditional on the number of serves, the number of winning serves, the number of left serves, and the number of right serves. Okay, so this conditional probability is the probability under the null that the server wins NLS serves to the left, conditional on winning NS serves in total after delivering NL and NR serves to the left and right. Okay, and here's the expression that Ronald Fisher came up with for this conditional probability. And the key thing about this expression is this probability, we can calculate this probability even though we don't actually know what PI is. Okay, so the right-hand side of this expression here doesn't depend on PI, okay, but we can nonetheless test the hypothesis that the probability winning for serves left and serves right are the same. Okay, and of course the formula at the bottom is just the CDF. Okay, so that's the Fisher exact test. How is it typically applied? So the Fisher exact test, we're going to reject the null hypothesis at significance level alpha after observing NLS serves to the left, winning serves to the left. We're going to reject the null if we get something that's at the tails, right? We're going to reject the null if we have very few winning serves to the left or if we have a whole bunch of winning serves to the left, right? Okay, so if we're out at the tails. Now an issue with this is that this test actually has size less than 5%. Because of the discreteness of the distribution, right? This is the number of winning serves to the left. It's not a continuous variable. It's a discrete variable. Okay, so if we can't just use this test straight, okay? For that reason and for another. Okay, so what we're going to do is we're going to use a randomized Fisher exact test. And this part is, I'm going to have to hand wave a little bit here. But so what we're going to do is we're going to observe a number of winning serves to the left. Okay, so we observe a number of winning serves to the left, and then we're going to draw a random test statistic, or we're going to generate a random test statistic, TI. TI is going to be if the number of winning serves to the left takes on its smallest possible value, then we're going to draw a test statistic from the uniform distribution on top. Okay, and if otherwise, we're going to draw a test statistic from a uniform distribution that's defined here, from this uniform distribution. Okay? Now, at this point, I'm not going to do a proof right now, okay? But under the null hypothesis that the winning probabilities for serves left and serves right are the same, and before the data is realized, you can show that this test statistic TI is actually distributed exactly uniform 0, 1. Okay? So it's distributed uniform 0, 1. Okay? And that has two consequences. So first of all, it means that if when we run the randomized test, we can do an exact, if we're interested in a 5% test, we can get an exact 5% test just by rejecting the null if the TI is less than 0.025 or if the TI is greater than 0.975. Okay, so now we have a test that's exactly 5%. Okay, yep.
But not so much data. The size is going to be pretty close to the level of significance in any case.
No, but we have, for any given point game, we don't have a lot of data, right? So you're right. We have hundreds of thousands of serves, but that's spread across many different matches. So for a given point game, we might have 30 serves in a given point game. So the discreteness is a problem, is an issue.
But why do you then care about the 5%? You could just do it, you could just use the size and not worry about the level of...
Yeah, but every test is going to have like...
Slightly different size.
Yeah, because exactly, every test. Also, this another important feature of this is that now we put all of the data on the same footing in some sense. For every point game, it doesn't matter how many serves there were, or winning serves or losing serves. Every point game we have is going to generate a test statistic that's under the null is a draw from the uniform 0-1 distribution. So it kind of homogenizes everything, makes them comparable. Okay, so we can let's take a first look at the data. This isn't going to prove it. We're interested in the joint hypothesis that the theory is true. So this data, what I'm going to talk about now, doesn't prove anything. Okay, but let's look at like men for first serves. We have 7,198 point games. For every one of those point games, we can run this test, and we can say, what's the frequency of point games where we reject the null hypothesis? Okay, and it turns out that if we do this, we reject the null hypothesis at the 5% level. We reject it at 5.06% of the time. Okay, so that seems encouraging. It doesn't prove anything, but it says that so the data at first glance, it looks kind of consistent with the theory. We're rejecting the null hypothesis at the correct rate. Okay, now we have to pause though for a moment, because remember, this is for a given point game. The test statistic is a random variable, right? So we might run the same test again, and we might, instead of not rejecting, we might now reject. Okay, so that means that when we run this test, what we should do is actually run this test. We're going to run these tests many times. So we have 7,198 point games. For each one of those point games, I'm going to run the test, and then I'm going to calculate the frequency that we reject the null, and then I'm going to do that 10,000 times. Okay, and so we see that we get, on average, it's 5.06. The average after doing it 10,000 times is 5.06%. We rejected the 5% level. And then this 0.16 number tells us the standard deviation of that number, right? Because, again, the percentage that we reject is itself actually a random variable. Okay, and we do the same thing for men for second serves, women for first serves, second serves, and again, at the 5%, 10% level, and what we see seems encouraging, right? In the sense that we're rejecting the null at rates that seem consistent with the theory being true. Okay, but this is individual point games. I want to know, and also another thing, by the way, is that when we run these tests, we're looking at the tails, right? I'm asking, how often do I see some extreme outcome where I have very few winning serves to the left, or a whole bunch of winning serves to the left? Right, so this table is only telling us about what happens in the tails. And remember, the theory, under the null hypothesis, the distribution of the t-values, they're actually uniform 0-1, right? The theory tells us the distribution, not just what's happening in the tails, it tells us about the whole shape of the distribution. Okay, so now let's come to the hypothesis that we're really interested in, which is that winning probabilities for left and right are equal in every point game, for all the point games. So how are we going to do this? This is a two-step process. The first step we've already talked about. For each point game I, we're going to form a test statistic Ti that's distributed uniform 0-1 under the null hypothesis. The second step is we're going to form the empirical CDF of the t-values for the n different point games. So for the n being, for example, the point games for serves by first serves by men. Okay. So under the joint null hypothesis, the theoretical CDF is just the uniform distribution, right? The TIs are distributed uniformly. And so now there's a nice test that we can use to test whether an empirical distribution is consistent with a theoretical distribution. It's the Kolmogorov-Smirnov test. And what that test statistic says, it says that look at the maximum distance between the empirical CDF and the theoretical CDF. Multiply that by that maximum distance by the square root of the sample size, and that test statistic has a known asymptotic distribution. Okay, so here we actually are, at this stage we are using an asymptotic distribution of the test statistic, but remember we have thousands and thousands of different point games in all of the tests we're going to run. Okay, so let me explain this picture. This shows a theoretical CDF in blue, okay, which is just the uniform distribution. It shows an empirical CDF in red, okay, and let me see if you can see my mouse. Yeah, okay. So what this shows is that, and this, by the way, is we're applying this test to the Walker-Wooders data, okay? So this is a test where we know we don't reject the theory when we use the statistical approach that Walker-Wooders used. Okay, so we have an empirical CDF of the t-values. This red line has 40-point games. Okay, Walker-Wooders only had data for first. Walker-Wooders had 10 matches, which means there's 20 servers. Let's see, 20 servers. Each server could serve from the add court or the deuce court. So we had 40-point games. We didn't have second serve, so we don't have 80-point games. Okay, so this red curve here has 40 steps. Okay, each one corresponding to a t-value. We can compute the test statistic, which is 0.67. We calculate a p-value, which is 0.565. So based on this empirical CDF, we don't reject the null hypothesis. Okay, and I've skipped ahead a slide by accident. Okay, so we don't reject the null when we apply the new test to Walker-Wooders data. Okay, but now you might say, correctly, that these t-values that you're using are actually random variables themselves. Maybe when you ran this test, maybe you just got lucky. If you ran it again, you'd get a different answer. Okay, and while that's true, if you run the test again, you'll get a different answer because the TIs are random. So what's our approach? We're going to run the test many times. Okay, every time we run the test, we get a p-value. Okay, and what I'm going to show you next is the empirical density function of the p-values. Okay, so this shows the empirical density of the p-values. We can look at the percentage of time that the joint null hypothesis is rejected at the 5% level. That's 0%. It's never rejected at the 5% level. Okay, at the 10% level, this is an empirical CDF after 10,000 trials. So at the 10% level, we see that actually we did reject the null hypothesis once at the 10% level. That means that it means that it is possible running this test to get a realization of t-values such that you actually reject the null. Okay, but it's a 1 in 10,000 possibility. So what we in fact see is that the mean p-value we get from running this test is actually 0.636. So the theory looks great, right? We have to be extremely unlucky when we draw these t-values in order to conclude, in order for us to reject the null hypothesis. Okay, so this test applied to Walker-Wooders data says that, okay, we get the same answer. The theory looks good. Okay, we don't reject the theory. Okay, now, of course, one reason for not rejecting the theory is that your test doesn't have any power, right? It's just like, for example, I could always just draw a t-value that from the uniform 0-1 distribution, ignore the data. Okay, just draw a t-value from the uniform 0-1 distribution. I'll reject the null 5% of the time. Always, right? Just because I'm ignoring the data. Okay, so let's see, does this approach that we're suggesting have any power? So what I'm doing now is applying the same test to the O'Neill data. And I'm asking whether the probability, in this case, I'm asking whether the probability that the player wins is the same when the player plays a joker card or a non-joker card. Okay? And what we can see from this CDF is, again, you see that there are way too many small t-values, right? So basically, like more than 20% of the t-values are bigger than 0.1, right? So there are way too many small t-values. Okay, so in this particular realization of the empirical CDF, the p-value is 0.01, so we reject. Whoops. Okay, but again, we can run the test many times, and with the O'Neill data, we can run the test 10,000 times. Every time, at the 5% level, we reject the null. Okay, every time. It doesn't depend upon, the randomness of the t-values doesn't make any difference. Okay, so this test will reject reject the mixed strategy play, looking at O'Neill's data, just as Brown and Rosenthal, for example, showed. Okay, so let me finally show you the data for tennis. Okay, this is looking at the Hawkeye data for first serves by men, this has 7,198 point games. So remember, the blue line is the theoretical CDF of the t-values. The red line is the empirical CDF of the t-values. Okay, they're very close. Let's zoom in on this a little bit, so we can see how close they are. Right? So they're very close. Okay. But again, there's this issue that, again, maybe I got lucky here, right? So we need to run the test many times again, and so that's what we do. So we run the test many times, and on the right-hand side, you see the empirical density function of the p-values, right? And again, we see that after 10,000 trials, there's actually one case after 10,000 trials where we reject the theory, okay? But you have to be exceptionally unlucky. Even at the 10% level, only in 0.14% of the trials do we reject. So the p-values are actually all distributed far to the right. I mean, they're all far away from the rejection region. So the theory is working great. Okay, any questions? Okay, I'll press on then. Let's see, how much time do I have?
I think this is time for another 5 minutes or so, 5 to 10 minutes.
Okay, let me just show, wrap up this little subsection. Okay, so if we can look at the data for second serves by men, okay, we get, again, the theory works very well, okay? For women, the theory works well, but not as well, okay? So for women, we actually reject, at the 5% level, we reject 44.7% of the time. So that means that it's almost like we're, roughly half the time we run the test, we would reject for women. Okay, this is first serves by women, second serves by women. Similar, the theory works well, but not perfectly. Remember, we have a lot of data here, right? So this test strongly rejects the theory when we have the comparatively small data set from O'Neill, and it doesn't reject for women that often when we have a much larger data set from professional tennis. Okay, and this is probably a good point to stop and address questions, if there are any questions.
So in the overlay results,
in the beginning, where at individual level theory didn't work, but at aggregate level it seemed to work. Was it a sheer coincidence of distribution of naive players? Can we infer something about aggregate behavior even if we have a mix of professional and non-professional players?
Okay, good. So you're making the point that okay. Thank you. Yeah. So in O'Neill's data, in O'Neill's experiment, the data in some sense looks pretty good in aggregate, but I believe if you actually test the aggregate distribution, it looks pretty good to the eye in aggregate. It actually, even at the aggregate level, it actually fails. Like if you test whether the aggregate distribution is consistent with being mixed strategy play, it fails. But I think what's happening, you see it more strikingly, the failure of the theory more strikingly at the individual level. But again, at the individual level, you have some people who say underplay the joker card and some people who overplay the joker card. So a lot of the heterogeneity that you see at the individual level, people doing weird stuff off in the fringes, actually it kind of averages out in some sense at the aggregate level.
but was this a coincidence, or you would expect when you have large set of heterogeneous players?
So the question, yeah, so was this a coincidence? I think it's not, I wouldn't call it exactly a coincidence. Yeah, because I would say that it's not an uncommon feature of experiments, that you do see a lot of heterogeneity at the individual level, that more heterogeneity that's consistent with theory. But yeah, I mean, my view is that, like, in some sense, in my opinion, economic theory very often works in some sense when applied, when it's tested experimentally. Theory kind of predicts qualitatively the nature of the data. Now, often though, the data doesn't exactly satisfy, if you do a classical, like, statistical test, often the data won't pass that test. But that's a pretty tough test. I mean, I've talked about mixed strategy play because mixed strategy play is an example where the theory actually often hasn't worked very well, even in the aggregate. So I think mixed strategy play is a high bar for experimental play, for laboratory play in the experiment. But if you look at, like, there are plenty of experiments about markets, for example, like Vernon Smith's stuff from the 60s where you do double auction experiments with buyers and sellers. The theory works fantastically, and it works fantastically well. It's not game theory, that's about markets, not games.
Win rates conform very closely to the data for men, but less closely in the case of women.
Yes.
Did you make that statement?
Yeah, so
is there a reason for it?
The question. The question is there an explanation for why the theory works better for men than for women? Although I would say it works well for both. But from the statistical, there are differences. And it turns out, and it's in the paper and it's in my other slides, is that what we can do is we can distinguish between let's divide women into the top women who are above the median rank, and the non-top women, who are also very good, but they're below the median rank. Okay? And we can do the same statistical tests on those two separate subsamples. If we do the statistical tests on the top women are just like men. The theory works fine for the top women. But if you look at the non-top women, then the theory is rejected for non-top women. So it's a difference. The theory is not working as well for women, but it's not working as well for women who are the non-top women. There are other reasons why, in tennis, I think there are other reasons why there's differences between men and women. The ball is served faster in men's tennis. Men are taller. So, I think there are different incentives to learn how to play, optimally if you're tennis that make it into our data set. And of course, the incentives to learn how to play optimally are very strong. Whereas in women's tennis, aces are less frequent, okay, and what's much more important in the play is the return and volley part of the play. Okay, so I think there are other possibilities. It could be that it turns out there are also differences in how serially correlated. Women servers are much more serially correlated than men are. So I think it's because, again, the incentives are different for serving in men's tennis and women's tennis. In men's tennis, the serve is a big advantage. And if I'm predictable, I'm going to suffer a lot. In women's tennis, the serve is less important. And if I'm predictable, I'm going to pay a smaller penalty. So I think that's the explanation, but there could be other explanations too.
Hello, sir. My question is regarding the O'Neill experiment.
Yep.
So you said that the structure of the game is such that it controls for the risk attitude of the player, even with if the payoffs are increased for subsequent hands. Yep. But I feel that if a player has some consequent wins, and I think that this will hold even stronger for increasing payoffs, won't the risk attitude change? Like maybe some case of a hot hands fallacy?
so imagine that they play twice. In the first hand they're playing for a nickel, and then in the next hand they're playing for $5, right? So 100 times the scale. So you could imagine all sorts of things, right? You can imagine that I might play a joker card at the first play because I want you to think I'm going to play joker again, and then I'll take advantage of you in the second play where it really matters. But all of that kind of reasoning is actually outside of equilibrium reasoning. That's not equilibrium reasoning. You can calculate the mixed strategy equilibrium, and it will say that you should play the O'Neill mixture at both hands, right? At both plays, the first play and the second play. So, that's not really a discussion of risk attitudes. So I don't know what to. I guess this is why we need theorems, because if you kind of think about it, it's not. Thinking about it in a less formal way isn't going to kind of deliver a definitive answer. So yeah, I mean, there's a theorem. You can go read the theorem, and maybe there may be behavioral assumptions that perhaps you could write down a behavioral model, but if we're sticking to classical game theory, then the result is the equilibrium mixture won't depend upon the stakes.
So friends, we have to close now because of time and time constraint. This has been absolutely brilliant. I mean, this is a clear example of how we need to think of theory and how it combines with empirics and actual experiments, and whether they actually converge or they do not converge. And well, this has been absolutely fantastic. Thank you very much.
My pleasure. Thank you.
Let's give a big hand to.
Sinha, our chairperson for today, to commence the session.
Thanks to the organizer, and it is very clear that they have really done a wonderful job, because the lunch was so good that people are taking a lot of time to move into the auditorium. Okay, so I believe all of them will join us shortly. Now, from the let me just again thank our three invited plenary speakers, John Wooders, Jordi Gali, and Joel Mokir. And the takeaway from the first session was that economic theory is good, and it can be as good as it can get. If there is a fault line, the fault line is with the data collection, the methodology, and not knowing enough about how to actually test a theory. Okay, so that's a very good news for the theorist here, and in particular for me, being an applied game theorist and industrial organization theorist. Okay, thank you all. May I now request Professor John Wooders to.
We're back. Okay, I've got sound too. Cool. Okay, so let me first tell you what we've done. So what have we done? We talked about mixed strategy play in the lab. We talked about a traditional laboratory experiment by Barry O'Neill. Okay. We also talked about data from the field, right? So we talked about, primarily I talked about this paper, about this new paper with using Hawkeye data with Roman Goriot and Lionel Page. What I want to do today is I want to talk about a couple of other papers. I want to talk about four papers. The first is a paper by Ignacio Palacios Huerta and Oscar Bolig, which is Experiencia Docent, which means experience teaches. Professionals play min-max in laboratory experiments. The second paper has a different story. The second paper says that is by Levitt Riley. It says that what happens in the field stays in the field. Professionals do not play min-max in the laboratory. I'm going to talk then about a paper of mine that looks at the data from the first paper and reevaluates the data. Okay, and then if time permits, I'll talk about another experimental paper that looks at essentially mixed strategy playing a poker-like game. Okay, so these papers are all what are called artifactual field experiments. Okay, so these are actually laboratory experiments with non-standard subject pools. Okay, so these are laboratory experiments where there's something, we're not just using regular students as human subjects, we're using somebody else as human subjects. Okay, so let me get started. So the Plasha Suerte paper. So what's the idea behind the paper? So we saw that professional tennis players behaved in a way that was consistent with mixed strategy Nash equilibrium in the field. And there's been other work that looks at soccer, penalty kicks in soccer, and it also argues that in professional soccer, players kick penalties in a way that's consistent with mixed strategy Nash equilibrium. So the idea of this paper is that if we take those soccer professionals and we bring them into the laboratory, will they take those skills that they've developed on the field, and are those skills transferable to the setting of the laboratory, right? Of course, the laboratory is quite a different setting. It's an abstract setting rather than, say, a physical penalty kick. Okay, and of course, if we find that it does, then if that behavior does transfer to the laboratory, that tells us actually that whatever we learn from laboratory experiments might depend very heavily on the kinds of people who participate in the experiment. So let me tell you about their paper. They recruited Spanish professional soccer players and university students to play the O'Neill game, and also a game that kind of was a stylized version of a penalty kick. Okay, I'm not going to talk much about the penalty kick. They had 20 soccer professionals 40 professionals in 20 fixed pairs. They played 200 rounds of the O'Neill game. The subjects didn't know the number of rounds. That'll come to be important later. Okay, and in each pair of players, one of the players, the role player or the column player, was a kicker, and the other player was actually a goalie. I'm talking about like their real life, and one was a kicker and one was a goalie. Okay, and the players were also from different teams, so they didn't have players from the same team playing against each other. And these were not the very best Spanish soccer players. These were players from what is called the Segundo League. So these are players who I understand, I'm not an expert on soccer, I understand that these are very good players. These are players who make a living playing soccer, but these are not players from like Real Madrid. Okay. They also had 40 students without soccer experience play in fixed pairs, 200 rounds of the O'Neill game. Okay, the stakes were larger. Remember, O'Neill had 5 cents. It was 5 cents per play. Here it was €1 per play. So a pair of players between them would divide 200 euros over the course of the experiment. So this took some money. Okay, and another departure from O'Neill's experiment was that how the actions were labeled. So they labeled the actions by colors rather than by ace, deuce, trade, joker, right? If you play cards, you know that joker and ace can have some special attraction. So to avoid like a joker effect where people play joker because the joker is an important card, they chose colors instead of card names. So I'll go straight to the data. This is the aggregate data this is the professional soccer players. This is their aggregate play. And this is kind of amazing. Look at so again, in red we have the theory. Okay, in red the theory, in blue we have the empirical frequencies. We see that the role player chose the one card in 0.201 or 20.1% of the time. Okay, which is almost the same as the theoretical frequency. Okay, and we see the same thing across the board, right? The joker card was chosen 39.8% of the time rather than the 40% that the theory predicts. So the differences are tiny, and indeed we can do a simple goodness of fit test to test whether the aggregate play is consistent with the mixed strategy Nash equilibrium of the O'Neill game. And if we do that, we get a p-value that's 0.91. So we're not even close to rejecting that. This data is like if you generated data under the null hypothesis, chances are it would be further away from what we see in the experiment. chances are that the data generated under the null hypothesis would not look as good as the data that was generated in this experiment. Okay, so this is very, very surprising data. Now, then we can look at the students as well. So the students actually don't do too bad either, right? The students, even we can, again, if we look at the frequencies, we see that the frequencies are roughly closely consistent with the theoretical predictions. And we also see that we get a p-value that's 0.273. So not only don't we reject the aggregate data for professional soccer players, we don't reject it in aggregate for students either. So of course we know that the aggregate data can look better than the individual data. So let's actually look at what the individuals in this experiment did. Okay, so at the individual level, the min-max multinomial model, so that's the model or the hypothesis that says that each player chooses the number card with probability 0.2 and the joker card with probability 0.4. So that hypothesis is rejected for 2 of the soccer players and 7 of the students. So notice that there were 40 subjects in this experiment. At the 5% level, we expect 2 rejections. If the theory is true, we expect to reject for 2 out of the 40 subjects. So this is bang on. The 2 rejections here is consistent, is exactly what we would expect for a sample of this size. On the other hand, for students, we observe 7. That's more than we expect for students. Okay. If we can also look at serial independence, whether the player's card choices, I'll call them card choices, even though they were actually choosing colors. The player's card choices were serially independent as predicted by the theory. And the answer is, again, we have 2 rejections for professionals, which is what we would expect. And we have more than the expected number of rejections for students. Okay. We can test a joint hypothesis. The joint hypothesis is all 40 of, say, the soccer players. All 40 of the soccer players choose their actions according to the multinomial, min-max multinomial model. And that null hypothesis is not rejected, not even close, right? You get a p-value that's closer to 1 than to 0. Okay? On the other hand, that model is rejected for students. We do reject the min-max multinomial model that all the students play according to min-max. We reject that with a p-value of 0.06. So the conclusion of Plaschers-Wertel-Wohlig is that, in fact, these skills that players develop on the field do transfer to the laboratory. So, we're economists, and so we're all skeptical, as we should be. Okay, when somebody says it's easy to prove, that you should sit up in your chair and say, well, maybe it is easy, but maybe it's obvious and in fact false. So you should, when somebody says it's easy to prove, you should pay attention. Okay, and when data like this comes along that looks as good as this data does, then it's worth maybe trying to replicate the results. Okay, and that's of course one of the beauties of experimental economics, or part of the beauty of experimental economics, is that when we get really striking, surprising results, we can actually replicate the results. Okay? We can run the experiment again. Okay, and that's exactly what Levitt, List, and Riley did. Okay, and their conclusion is right in the title of their paper. Okay, their conclusion is that what happens in the field stays in the field. Professionals don't play min-max in the laboratory. Okay, this is a replication of the Plaschers-Wertel study. Now, of course, the replication is going to be slightly different, right? In the sense that, they did not recruit Spanish Segundo League players for their experiment. Okay, and so we'll have to discuss. In some sense, you can never really literally replicate exactly something because, if nothing else, your replication is going to come later than the original work, right? Okay, so we'll have to think about whether the differences were important or not. Okay, so let me tell you about what they did. They recruited various kinds of professionals and students to play the O'Neill game and also another game called the Pursuer-Evader game, a mixed strategy game that I'm also not going to talk about. Their subjects played in fixed pairs for 150 rounds, but switched roles after 75 rounds. And the O'Neill game was actually played with regular playing cards. Here they use spade, heart, club, and diamond rather than ace, deuce, trade, joker. Okay. They used, regarding the subjects, they had 24 UVA, University of Arizona College students. They also had various kinds of professionals. There were 22 bridge players. There were 52 poker players. These poker players were people who they were recruited at the 2006 World Series of Poker. But what I'm going to focus on is the soccer players. They had 32 professional soccer players from 3 major league soccer teams, the Los Angeles Galaxy, Chivas USA, and Real Salt Lake City. In the case of the soccer players actually played the game. The experiment was conducted in the laboratory, in the locker room, sorry. Okay. Yeah, this is, and they also had some subjects play against a computer that was following a min-max or a non-min-max strategy, but let me not talk about that. Okay, the bottom line is that the Plaster-Suerte results failed to replicate in the Levitt-List-Riley experiment. Let me just show you a table from their paper. So let's look at, say, that this is Plaster-Suerte over here on the right. This is Levitt-List-Riley on the left. Okay, remember we can test for min-max play at the aggregate level. Plaster-Suerte, they get p-values of 0.956 for the row, 0.932 for column, and joint play, row and column, 0.91. So the p-values are nowhere close to rejection for the Plaster-Suerte Volig soccer players. Okay, on the other hand, Levitt-List-Riley, when they run the same tests on the soccer professionals, the poker players, the college students, all of these things are rejected at any level of significance, right? So the theory is decisively rejected for the Levitt-List-Riley subjects, for all of the different kinds of Levitt-List-Riley subjects. If we look at individual play, remember that Plaster-Suerte and Volig had, at the individual level, they had rejection rates that were exactly the expected rejection rates of 5%. Okay, whereas the soccer professionals for Levitt-List-Riley, 28% of the soccer players, the theory is rejected for when they're in the row position, 16% at the column position, and 31% overall. And finally, if we look at runs, we see these are runs tests. These are tests for serial independence. Okay, Plaster-Suerte and Volig, they rejected at exactly the 5% level. Pardon me, they had a number of rejections that was exactly consistent with the theory, 5%. Okay, but Levitt-List-Riley actually observed too many runs they reject for 16% of their subjects. Okay, so much more. Okay, so the Levitt-List-Riley paper fails to confirm or fails to replicate the Plaster-Suerte findings. Now, why could that be? Well, one reason, I think Plaster-Suerte and Volig would argue, is that soccer players, American soccer players, are not comparable to Spanish Segundo League soccer players. I mean, Americans actually can't play soccer. That's at the European level, okay? So that's a possibility. So maybe Major League Soccer players aren't actually comparable to Spanish Segundo League players. Okay, and there are some other differences that we saw there are some other differences in the replication between the replication study and the original, right? So for example, in the replication study, the soccer players, the experiment was conducted in the locker room rather than a laboratory. Okay, it was conducted by players on the same team, okay, because it was in their locker room versus players drawn from different teams. Okay, and so those are indeed differences. On the other hand, the Levitt-List-Riley results, Levitt-List-Riley don't really find anything in terms of skill transfer from the laboratory to the field. Right? You can imagine that some of these things might have some significance, but Plaster-Suerte Volig find that these skills transfer almost perfectly from the field to the lab, and Levitt-List-Riley don't find anything at all. Okay, so what I'm going to talk about next is another approach. Is a paper that re-examines the Plaster-Suerte Volig data. Okay, so I didn't run another experiment. I just looked at their data again, and I'm going to argue that even if we look at their data, their data actually is inconsistent with mixed strategy play in important ways that they didn't discover when they wrote their paper. Okay, so what do I mean precisely? So this is the paper. This re-examines the data from Flash to Swerte-Volig. Okay, so the behavior of the professionals appears to conform extraordinarily well to the theory in the Plaschs-Swerte-Volig experiment. But notice that the test that I told you about, testing whether the players are choosing cards according to the min-max multinomial model, that's really looking at just the tails. Okay, it's looking like how many players are far away from how many players is their play far away from what's expected, right? Those are the players we reject the theory. But the theory, the theory of mixed strategy Nash equilibrium doesn't make just a prediction about how people are or how play is distributed in the tails. The theory makes a prediction about how play looks in the aggregate. It makes a prediction about the distribution of play across the different cards. Okay, and that's what I'm going to focus on. Okay, and so we can ask, is the distribution of card frequencies consistent with the theory? Okay, and I'm going to show you that for the O'Neill data, it's not, and it's not in ways that are somewhat surprising. Okay, so we saw a picture well, we actually saw this slide earlier. So let me remind you. This picture is O'Neill's data. He had the subjects play 105 times. If the joker cards chosen with probability 0.4 each play, then we expect 42 joker cards to be played. Okay, and we see that this red bar here, the red bar here shows the number of players or the frequency of players who chose either 41, 42, or 43 cards. So the frequency of players who are very close to expected play, which was 42. Okay, and the theory says that about 23%, the theory says that of mixed strategy Nash equilibrium says that 23% of the players, we expect to see 23% of the players whose actual number of card choices is within one of the expected amount. Okay, and as we talked about this morning, if what we see in O'Neill's data is that there's too much heterogeneity in the play of the joker card. There are these players down here who are playing the joker card too infrequently to be consistent with theory, and there are players over here that are playing the joker card too frequently to be consistent with theory. Right? We should have, of course, it's a mixed strategy experiment. We expect some players are going to play the joker card more than 40% of the time, and some joker cards are going to play less than 40% of the time. Some players are going to play the joker card less than 40% of the time. But O'Neill's data, we see too much heterogeneity. There's too much in the tails. Okay, let me show you the Plaschs-Swerte-Volig data. Okay, now again, the theory, they had 200 plays. The joker cards played with probability 0.4, so we expect, on average, that a player would play the joker card 80 times after 200 plays. So what this shows, here's a bin. It has 79, 80, and 81. This shows us the frequency of players who, after 200 plays, were within one card of the expected number of cards, which was 80. Okay, we expect, the theory, of course, tells us what the distribution is of the number of joker cards played after 200 rounds. And the theory says that we should see about, out of 40 players, we should see 6.85 players who are within one card of the expected number. What do Plaschs-Swerte-Volig actually have in their data? They have 16 of their 40 players are playing within one of the number of expected joker cards. This is far more than we would expect if the theory is true. Okay? In fact, if the theory is true, the odds of having 16 or more out of 40 players playing the joker cards within one of the expected number, the odds of this happening, if the theory is true, are about 1 in 1900. Right? We can calculate that under the null hypothesis. Okay, so we actually see what we have here is like the opposite of what O'Neill saw in his experiment. In his experiment, there was too much heterogeneity. Here, there's not enough heterogeneity. There's not enough dispersion in the play. In other words, the play we observed in the data is actually closer to expected play then we would expect to see if the theory is true. Okay, so let's look at the other cards and see what's going on. So now I'll look at again, in red we still have the theory. Okay, so the theory here shows in red we have the theoretical, the expected number of cards in this bin, okay, under the null hypothesis. And the other bars, the blue bar, for example, shows the frequency of players choosing the one card. And we see, for example, that there are 21 of the 40 players, more than half of the players actually chose the one card within one of the expected frequency, right? The one card is played with probability 0.2, so we expect it to be played 40 times after 200 plays. And we actually have 21 of the 40 subjects who are within one of the expected number. Again, this is much more than we would expect under the theory. Okay, so I haven't done any statistical tests yet. I will tell you some, but when we look at the data, we see that the data actually doesn't look consistent with the theory. And the results, the statistical tests that I told you about earlier, those are focusing entirely on what's happening in the tails, right? The statistical test I talked about, where we don't reject the theory, it's saying that the number of rejections, the number of players who are too far from the expected, the play in the tails is consistent with the theory, right? It's only looking at the tails, but if we look at the whole distribution of play, we see that something is surprising. Okay, so as I said, for professionals, their empirical card frequencies are too close to expected frequencies. The problem is, imagine we had a bag of coins, a bag of fair coins, okay? Let's say a bag of coins. We want to test whether these coins are fair coins. So we take one by one, we take the coins out of the bag, okay, and we toss the coins 100 times. And we know that a fair coin, the expected number of heads is 50. Okay, so if I start taking coins out of the bag and I'm tossing them 100 times each, the first coin, it comes up heads 50 times. The second coin, it comes up heads 50 times. And so on. I do this for all the coins. They're coming up heads 50 times. I never reject the null hypothesis. I never reject the null hypothesis that the coins are fair. Okay? I reject the null when I observe a whole bunch of heads for a particular coin or very few heads. Okay, but clearly there's something strange about a bag of coins where all of these coins are coming up heads exactly half the time. Now, of course, in this data, it's not as extreme as the coin problem I just described to you, but it's of the same character. Okay, so let's look at the students in Palacios-Huerta-Bolig's experiment. Okay, for students, the distribution of play actually looks kind of closer to the theory than it did for the professionals. For student subjects, we don't see the huge spikes at expected play that we saw for the soccer professionals. Okay, and for the number cards, we do see a little bit more of the number cards concentrated around the equilibrium expected frequencies than the theory, but it's not that striking. It's certainly nothing like the Palacios-Huerta-Bolig. Okay, so in summary, students don't have a tendency for actual play to be too close to expected play. Okay, rather there tends to be too much heterogeneity in the empirical card frequencies. So again, let me back up. I'm trying to back up. Every way seems forward here. So, okay, hang on. There we go. So again, if looking at the students, we do see, for example, we see a bit more play of the one card too infrequently, or a bit, we see too much play of the two. We have a couple of instances where there were too many plays of the 1, 2, or 3 cards. So there's a tendency to observe behavior in the tails for students that we don't see at all for the professionals. Okay. So now, I haven't, all of that though doesn't actually test. There's nothing, that's just eyeballing the data. That's looking at the, that's we're seeing that something's unusual about the data, but it's not, it doesn't, we haven't actually done a statistical test, but we can do a statistical test. So we can apply the Kolmogorov-Smirnov test that I talked about earlier this morning. We can look at whether the distribution of p-values for professionals and students is consistent with the min-max hypothesis or consistent with mixed strategy play. Okay, so we're going to test, as I said, whether the distribution of card frequencies across players is consistent with equilibrium. So there's some, we can write Nij as the number of joker cards played by subject I after 105 rounds. And we have a CDF for the number of joker cards after 105 rounds under the null hypothesis. I can form a random test statistic in the similar way that I talked about this morning. Okay, why am I forming a random test statistic? In here, I'm doing it just because the Kolmogorov-Smirnov test assumes that it assumes that the data is generated by draws from a continuous distribution. It doesn't matter what distribution it is, but it has to be a continuous distribution. So when I follow this procedure, I get the data is actually, the draws, the TIs are uniformly and continuously distributed under the null hypothesis. Okay, and again, you're gonna have to take my word for that. There's a proof in the paper. Okay, so, and let's see, so yeah, so the chaos test, this is the PIs. From the T's, I can compute p-values. When the p-value is near 1, then we're getting the result. When p-value is near 1, then we're getting a number of cards that's consistent with, that's close to expected play. And when it's near 0, then we're far from the expected number of cards, far from the theory. Okay, so let's look at the play of the joker card in O'Neill's data. So I'm gonna start out slow. I'm gonna apply this test to O'Neill's data. Okay, O'Neill didn't do this test, but here it is. Okay, so this is the CDF of p-values that, again, under the null hypothesis are uniformly distributed. So the black line here is the theoretical CDF. Okay, and we're going to compare that to the empirical CDF of the p-values. And what I want you to notice is that there are way too many small p-values, right? Like, so for example, like over maybe 30% of the p-values are let's see, 30% of the p-values, so I can, at a p-value of 0.1, I can go up to here, and this tells me that maybe more like 35% of the p-values are actually below 0.01, right? That's how to interpret the empirical CDF of p-values. So, of course, we should only have we should only have 10% of the p-values under 0.1 and 20% of the p-values less than 0.2 and so on. So when we look at the O'Neill data, we can actually see that there are too many small p-values, and this is telling us what we already know, right? This is telling us that when it comes to the joker cards, we have too many players who are playing the joker card either very infrequently or playing it very frequently. We have too much heterogeneity in the tails for play in O'Neill's experiment to be consistent with mixed strategy Nash equilibrium. But notice that we're not just looking at p-values that are less than 0.05 here, right? We're looking at the whole distribution of p-values. So we're not focusing on the tails entirely. We're looking at the whole distribution of p-values and therefore the whole distribution of play. Okay, and so we can compare these two CDFs, the theoretical and the empirical, and we can see that they don't look close. And we can execute the Kolmogorov-Smirnov test, right? That test, as I said this morning, it looks at the maximum distance between the empirical CDF and the theoretical CDF. You multiply it by the square root of the sample size. Okay, you get a test statistic that has a known asymptotic distribution, and we can calculate the p-value. We get a p-value that's basically 0. Okay, so we're using this test to see what we already saw before for the O'Neill's data. For O'Neill's data, which we can reject equilibrium play on O'Neill's subjects. Okay, so this is again still O'Neill's data. But for the non-joker cards, and we can reject for each card we can construct we can test the hypothesis that the player is choosing that card with the equilibrium probability. So for the number cards, we can test the hypothesis that that the one card, say, is being chosen with probability 0.2. Okay, and we can reject that the distribution of p-values for the one card is consistent with the theory. We can reject it for the 2 cards. We don't reject for the 3 card. Okay, but the point is that basically if we look at what we see for the joker, we also see for the number cards. The theory is rejected on O'Neill's data. Okay. Okay, so let's now use the same test. Let's look at the same test, the chaos test. Let's apply it to Placis-Ware-de-Wohlig's data. Okay, and we want to see whether the distribution of p-values for professionals and students is consistent with the min-max hypothesis, or mixed strategy Nash equilibrium play. Okay, so this is the picture of, so again, the theoretical CDF is the 45-degree line. In blue, I have the empirical CDF of p-values for the Placis-Ware-de-Wohlig professionals, and in red, I have it for students. Okay, notice that there's one difference is between professionals and students is that for students, this bit here tells us that we have too many small p-values for students, right? Because the empirical CDF is above the 45-degree line. Whereas for professionals, where we see the biggest departure of the theoretical and the empirical CDF is for large p-values, right? This says that if we look at like p-values of 0.7, only maybe 60% of the p-values are below 0.7. So that means that 40% of the p-values are above 0.7, which is more than we expect, right? Okay, we'll come to we can do this, we'll do the test in a minute. I'm just showing you the empirical CDFs for the data. For the 1 card, we saw that the 1 card was kind of extraordinary for the Placis. 21 out of 40 players played within 1 of the expected number of 1 cards in the Placis-Ware-de-Wohlig data. So here, it's very evident that we have way too many large p-values, more than we expect for professionals, right? So again, here we have like something like 60% of the p-values are above 0.08. We only expect 20% of the p-values to be above 0.08. For students, actually, again, we see too many small p-values, but the rest of the distribution is pretty close to the theoretical distribution. Okay, so this is the 1 card. I won't go through, I'll do the rest. This is the 2 card. Again, notice that the red curve for students actually look better than professionals in this, right? The empirical CDF for students is closer than it is for soccer professionals. Okay, the same here, okay? Okay, and then of course we can test. Then the final model is not to just focus on a single individual card, but look at play of all 4 cards. So this is the min-max multinomial model. Okay, the null hypothesis here is that each player is playing each of their cards in the equilibrium with equilibrium probability. Again, for students, we see this departure from equilibrium with there are too many low p-values. But for professionals, we have this wild departure, which is there are too many large p-values. Okay, so if we actually, these tables just report the statistical tests, right? So we can I didn't put it on the slides, but for say the Joker card, for the for the soccer players, we can test whether they're choosing the Joker card with probability 0.4, okay, and we reject that, right? We get a p-value of 0.02. This is again, we reject it because the empirical CDF of the p-values is too far from the theoretical CDF of p-values. We do that for the Joker card for soccer players, the 1, the 2, the 3, every card we reject. Okay? Okay, and for all 4 cards jointly we reject for the soccer players. But for the student subjects, yes, we also tend to reject for the Joker card and the 1 card. We don't reject for the 2 or the 3. We're at the margin here for the all four cards jointly. So my point is that if we do this statistics, what Placis-Ware had us do, Placis-Ware-de-Wohlig, they had us look just at the, I've got to find the right spot here. They had us look at just the tails. And the tails look, the behavior in the tails is consistent with the theory. But if we look at their data, we see that the behavior in their data, the behavior in their data is not close to consistent with the theory if we look at the whole distribution of card frequencies. Okay? Okay. Okay, so this is a puzzle. If somebody handed you a bag of coins, and all of these coins, when you took these coins out and tossed them, they all turned out to be fair coins. Not just fair coins, they all turned out that every time you tossed each of these coins, they came up heads 50% of the time. You'd wonder, how is this possible? What kind of coins are these? Okay? So this issue with this issue was pointed out to them by a referee. Okay, and in the paper, this is what they say about it. In the paper, they say that the excessive closeness of the observed frequencies to the hypothesized one suggests that subjects do not randomize, but rather they try to match some probabilities that they have consciously or unconsciously in mind. Okay? So what are they saying? They're saying that these Spanish Segundo League soccer players, they come into the lab, they look at this game, they look at the O'Neill game, and they understand intuitively that you should play each of the number cards with probability 0.2, the joker card with probability 0.4, okay? But they make a mistake too. They also they instead of just choosing the cards at those frequencies, they actually try and match those frequencies as they play, right? So the analogy here is that you come in, you ask somebody to play matching pennies, okay? Matching pennies, you should mix 50-50 between heads and tails, theoretically. So I think it's plausible for matching pennies. I won't explain the game. Hopefully everybody has heard of it. Matching pennies is a simple game where you mix between heads and tails with probability 0.5. That's the obvious way to play this game. It's like paper, scissors, rock, right? In paper, scissors, rock, we know that we should play each paper, scissors, rock, each with probability a third. Okay, but now an unsophisticated player might say that they want to actually match the 1/3 frequency. They might say, as they're playing paper, scissors, rock multiple times, they might play in a way so that their frequency of paper never departs too much from a third, right? They have some understanding, but they have a limited, in fact, incorrect understanding, right? You know, if you're playing paper, scissors, rock, and you're playing the equilibrium mixture, some of the time you're actually not going to play rock for a long time, right? That's how it goes, and you know, you don't. The frequency that you play rock may actually depart from a third. It might depart from a third quite a bit for some periods of time. We know that in the long run, it's eventually a third. Okay, so, but they're saying, Plascheswert of Oleg are saying here that these players come into the lab, it's obvious to them how they should play, which I think is implausible. Okay, and not only that, they play in the wrong way. They don't play it. They try and match the card frequencies. They try and make sure that at any point in time, about 40% of their card choices have been the joker card. Okay, that's what they're asserting. So let's take a look at their data and see whether that is actually plausible given their data. Okay, so first of all, imagine, let's go back to rock, paper, scissors for a moment. If I'm trying to match the card frequency, the action frequencies in rock, paper, scissors, I can do that easy. I can do rock, paper, scissors, rock, paper, scissors, rock, paper, scissors, okay? And that way, I'll never get too far away from a third, a third, a third. Okay, but if I do that, I mean, obviously I would be exploitable, but let's put that aside. If I do that, I would actually, there would be serial correlation. I would be switching direction. I would be switching my choice too frequently. Right? I would never be playing rock twice in a row because I'm going rock, paper, scissors, rock, paper, scissors. Okay? I would never have a long run of rock. Okay? And so if I were trying to match the choice frequencies in rock, paper, scissors, I'm going to have serial correlation in my play. Okay? Because I'm switching choices too often. But we know that, so the first clue that can't be the explanation of Plascheswert of Oleg data is that, in fact, they don't find serial correlation when they look at the soccer players, right? They reject serial correlation. The null hypothesis of serial independence is rejected at exactly, for 2 out of the 40 players. It's rejected at exactly 5% of the players, as we would expect if they're truly serially independent. Okay, so let's think about another way of approaching this question, right? If the professionals are actually matching the min-max frequencies, as Plaschers-Werther-Wohlig suggest, then I should be able to just cut the data in half. If I cut the data in half, then I'll find that they're close on the first half, and they're matching frequencies on the second half as well, right? Because they're matching frequencies over the whole course of play. Okay, so with the features that we saw when we looked at the aggregate data, we should see, in particular, the fact that actual play is too close to expected play. We should observe the same thing when we look at, say, the first half of the data or the second half of the data. Okay, so in other words, just another way to say that is there should be too many large p-values in the empirical CDFs of p-values for both the first half and the second half. So let's look. Okay, so let's look at the first half. So this is, remember the subjects, by the way, they didn't know how many hands were going to be played. So they don't know what the first half is, the subjects. So let's look at the first 100 plays. We can look at let's just focus on the play of one card at a time. Let's focus on the joker card. Okay? So the null hypothesis that a joker card is played with probability 0.4, that's rejected actually for 7 of the professionals. Okay? By professionals, I mean soccer players, right? But only 2, again, only 2 is expected. For the first students, it's rejected for 6. Okay, so the first half is already looking different from the overall data, right? Because remember in the overall data of 200 plays, we only rejected for 2 soccer players out of the 40, but when we look at the first half, we reject for 7 out of the 40. Okay, and we see the same thing for the 1, 2, 3 cards. So let's see, for students, we still see that the joker card is we reject the null for 6 of the students. So let's see, that's a 6 instances or a professional, 6 expected. Okay, but if we look at the min-max multinomial model, so again, they're choosing all 4 cards at the equilibrium frequency. That's the null hypothesis. We reject for 3 professionals and 3 students. Okay, so if we look just at the first half of the data, and we look at the same test that Plaschers-Werther did on the whole data set, but we just focus on the first half, there actually doesn't seem to be much difference between soccer players and students. Okay, they both depart from equilibrium play at the same. We reject the null hypothesis for these various tests at the same rate for both groups of subjects. The second half is another 100 plays, and again, let me focus on the professionals. We can ask: are the professionals in the second half playing the joker card at the equilibrium frequency? Well, again, we can reject that for 7 of the soccer players. Okay, when we only expect to reject for 2. Okay, so on the second half as well, on the second half of the data set as well, students and soccer players look very similar in terms of the results of these statistical tests. Okay, so we can look at a bunch of different kinds of tests, right? We can look at all of these x's here are rejections of the theory of one test or another, right? So the x here means that if we look at soccer professionals, if we look at the first 100 plays, we can reject that the column players are choosing the 1 card, with the 40 soccer professionals are choosing the 1 card at the equilibrium frequencies. We can reject that. Okay, and we can reject that in the first half for the column players for the number 2 card as well. So all of these x's here correspond to just rejections of the theory based on the first half on the left-hand side and the second half on the right-hand side. And if we contrast that with the students, you kind of see that, in fact, if we just doing the usual standard tests, we're rejecting the theory much more for the soccer professionals than we are for the students. Okay? Okay. So there's something, whereas again, going back to the beginning, if we look at the whole play, if we look at all 200 plays, then we reject, then we see a difference between students but the difference is that the professionals are playing, and we don't reject for professionals, but we do reject for students. Okay, so those were all tests that looked at the tails. We can again look at the whole distribution. So this is again for the first half, the empirical CDF of p-values for the joker cards. So again, when the line is close to the 45-degree line, that means the data is closer to theory, closer to the theoretical benchmark. Okay, we have professionals and students. For the first half, for the one card, professionals in blue, students in red. Here there's maybe a little difference between professionals and students here in favor of the professionals. Okay, pardon me. Yeah, in favor of the professionals being closer to theory. Okay, the 3 card, very similar for professionals and students. Okay, and again, if we look at the KS test, again, the KS test is based on the whole distribution, not just the tails. For the KS test, the students and professionals look very similar, right? So yeah, we marginally reject for the 1 card for the professionals. We reject for the joker card for students, but if the joint hypothesis that a player is choosing all their cards according to the equilibrium frequency, we actually don't reject that for either professionals or students. So very little difference between professionals and students. Okay, what's the story in the second half? Okay, the second half, it's kind of the same story as the first half. So again, this is the empirical CDFs. I'll go through the slides quickly, but I just want to point out that these CDFs are close for students and professionals. There's not much difference, and they're both fairly close to the theoretical benchmark, which is the 45-degree line. This is the 2 card, the 3 card, okay? And again, we don't use it, if we look at the whole distribution of play, on the second half, we don't reject for either professionals or students. Okay, again, the data looks very similar. So, but what does that tell us? Remember that, why are we doing this? Well, Plastic-Square-Dvorak told us that their conjecture was that professionals were choosing their cards to match the equilibrium frequencies as they played. So that if that's true, then for professionals, we should see too many large p-values in the first half because actual play is too close to expected play. And we should see too many large p-values in the second half as well because, again, actual play will be too close to expected play. But we don't see that. So that tells us that the Plastic-Square-Dvorak explanation for why their data has this unusual feature that actual play is too close to expected play, their explanation, it doesn't work, okay? So that is not actually explaining what's going on with their data. So, what are the professionals actually doing? Okay, how is it that the professionals look so much better than the students when I look at all 200 rounds, okay, but professionals look just like students when I look at the first half or the second half? Well, how is that possible? Okay, well, I want to look at the first half and second half choice frequencies. So let me give you a different kind of table. Okay, so this is on the horizontal axis. I have the first half frequency of joker, and on the vertical axis I have the second half frequency of joker. Okay, so and of course the base. This is centered around 0.4, right? This is the theory, and under the under equilibrium play, there should be no correlation between the frequencies, the first half frequency and the second half frequency, right? Under equilibrium play, I'm going to choose joker 40%, with probability 0.4, and maybe in the first 100 rounds, I choose the joker with probability less than 0.4, but that doesn't tell me anything about the frequency of joker in the second 100 rounds, because again, under the theory, my plays are independent, okay, of what happened in the past, right? At every round, at every play, every single hand, I choose the joker card with probability 0.4. So under the min-max under equilibrium play, these pairs of frequencies should be completely uncorrelated. Okay, let's just think about a particular point. Right, this guy right here. This guy is somebody who in the first half, they played joker with probability less than 0.4, right? Less than 0.4. But in the second half, they played joker with probability more than 0.4. Okay, so everybody in this quadrant switched. They underplayed joker in the first half, and then they overplayed joker in the second half. Everybody down here did the opposite. These were people, like this guy here is somebody who overplayed Joker in the first half, but then underplayed Joker in the second half. Okay? So they played Joker more than 40% of the time in the first half and less than 40% of the time in the second half. And that can happen, of course, right? We expect. This is no surprise that, you just because you play Joker with probably, you happen to play Joker with more than 40% in the first 100 plays, you might play Joker more or less than 40% of the time in the second 100 plays. But what's a puzzle here? Let's look at the rest of this picture. So this line here, this is actually is a line of slope -1. Okay, and then this is just a simple-minded. The dark line here is a simple-minded regression line. Okay, and all that line is there for is just to help you see that, in fact, subjects who underplay Joker in the first half, they switch to overplaying Joker in the second half. Right? There's negative correlation in their Joker frequencies between the first and the second half of the experiment. And conversely, people who overplay Joker in the first half, if they overplay Joker in the first half, they underplay Joker in the second half. Okay, so they're not at all doing what Plaster-Square-Tervolling suggest. Okay, they're actually switching. If I overplay Joker in the first half, I'm going to underplay it in the second half, and vice versa. Okay, and there are fewer players. There are, of course, some players who underplayed Joker in both halves and overplayed Joker in both halves as well. Okay, but overall, the picture we don't need to run a regression, although it's there. This picture tells us that, in fact, there is a negative correlation between first half Joker frequency and second half Joker frequency. Okay, and what is the implication? If you overplay Joker in the first half and underplay it in the second half, well, on average, you're going to be closer overall than you were in either half. Okay, you're going to be closer to the 40% frequency overall. Okay, so let's look at the other cards. Okay, this is just the Joker card. Again, theoretically, there should be no correlation here. These should be uncorrelated under the null hypothesis of equilibrium play. If we look at the one card, well, that's pretty striking, no? So almost all of the players, if they overplay Joker, they switch between overplaying and underplaying, or vice versa. Right? There are very few guys. These guys are overplaying Joker in both halves. And that means, of course, over 200 plays, that means they're going to overplay Joker. They're going to, overplay the one card. They're going to overplay the one card when we look at all 200 rounds. And these guys, this guy, or these two people, they'll underplay the Joker card when we look at all 200 rounds, because they're not underplaying in each half. But notice the striking negative correlation, right? This is what it means to be, this guy here is exactly on the 45-degree line, or the -1 line. This guy underplayed Joker in the first half. He overplayed Joker in the second half, but he was exactly 40% Joker over 200 rounds. That's what it means to be on this line with slope -1. Okay, that's the one card. The two card, again, we see, and just the regression line is there to help us, a visual aid. Again, it looks like negative correlation. Most of the subjects are switching between underplaying and overplaying. Okay, the three card, same story. Well, we can actually do tests. We can test whether we can calculate this Spearman rank correlation coefficient, and we can test whether these first and second half frequencies are uncorrelated as the theory says that they should be. Okay, and for the professionals, we can reject for every card. We can look at every card one by one. We can reject the null hypothesis that their first half play is uncorrelated with their second half play. Okay, so inconsistent with the theory. And also notice that the sign of the correlation coefficient. The sign of the correlation coefficient is negative. Okay, that tells us that overplayers become underplayers and underplayers become overplayers. Okay, which is not obvious why that would happen. Let's look at the students. If we look at students, we can reject the correlation coefficient being 0. For the Joker card, for example, where we get a p-value of 0.07 for the one card. But notice that when we do reject, only for those two cards, when we reject, we actually get positive correlation. So for the students, There are some students who overplayed Joker in the first half, and if they did, they tended to overplay Joker in the second half as well, which seems plausible, right? They get the game wrong, right? So they're not switching. Okay, so okay. So what have we seen? We've seen that professionals, inconsistent with the theory, they follow non-stationary strategies, non-stationary mixtures, and they switch. And what happens when they switch? Well, switching is going to reduce the variance, right? So if I toss a fair coin is tossed 200 times, the variance is 50. Okay. If I have a coin which is heads with probability 0.5 plus gamma in the first 100 tosses, and it's heads with probability 0.5 minus gamma in the last 100 tosses, then the variance is going to be smaller. Of course, in both cases, the expected number of heads is the same, but in the latter case, it's by switching play that we actually get actual plays too close to expected play. Okay, I haven't talked about the penalty kick game, but the penalty kick game is a 2x2 game where it's also mixed strategies. And again, if you look at it's not as striking for the penalty kick game, but again, the correlation for the in first and half choice frequencies is present. It's negative. Those professionals are also switching. Okay, whereas we don't for students. Students are actually close. Students are not switching. There's no evidence that students are switching between the first half and the second half. Okay, which is consistent with the theory. So we have a puzzle. Okay. Why do professionals follow non-stationary mixtures? Okay, well, okay. Here I don't know the answer, okay? But here are some conjectures, right? You could imagine that there are strategic considerations, right? The role player might overplay the Joker card in the first half with the idea that he can then induce his rival to overplay the non-Joker cards and then take advantage of him in the second half, okay? Okay, so let's see, is that right? Let's think about that. So I overplay the Joker card. If I overplay the Joker card, then I'm going to push my opponent as a role player. If I keep playing Joker, 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 the column player is going to figure that out, and he's going to switch to one of the number cards. Okay, and then in the second half of the experiment, I could now switch to the number cards and take advantage of him while he's now locked in on playing the number cards. Okay, could happen. I guess I would point out if that's the explanation for the data, then this data is inconsistent with equilibrium play because that's not a mixed strategy Nash equilibrium to behave that way, right? Okay, if a player is playing in a way to achieve, if a player is playing this way, then they're not playing the mixed strategy Nash equilibrium. Okay. Okay. Also, it's not obvious if someone were to play that way. It's not obvious why that would somehow lead them to playing the Joker card 40% of the time over the whole course of the experiment, okay, which is what we see too much. Okay, another possibility is that there was actually some flaw in the conduct of the experiment, right? So remember, this is an equilibrium in mixed strategies. In equilibrium, a player is indifferent over all of his actions by definition of a mixed strategy Nash equilibrium. So you can imagine that the experimenter is sitting next to the subject, and the experimenter notices that a subject is maybe playing the Joker card too frequently, and the experimenter might somehow provide a cue or a hint to the subject to play Joker less frequently. The experimenter might have a look of disgust on his face or something that might discourage the player from doing what they're doing already. Okay, so yeah, so again, if a player is indifferent, it might not take much to actually induce them to play differently, right? It's a possibility. I don't know. So, what have we learned? Well, we've learned first of all, Plascius Huerta claim that experience from the field translates or transfers to abstract normal form games in a laboratory? I don't believe that claim. Okay? I don't believe that claim on the basis of, first of all, that result cannot be replicated. The Levitt-List-Riley experiment did not even come close. The Levitt-List-Riley provided no suggestion in their data that somehow that the soccer professionals were played closer to equilibrium than student subjects. More importantly, Plascher-Huerta-Wohlig's own data is inconsistent with mixed strategy play. The only way that the reason they failed to realize that is because they looked just at behavior in the tails. Okay, they don't see. They observed the behavior in the tails is consistent with the theory. There are two professionals who departed from equilibrium play of the Joker card by enough that we could reject the null hypothesis that they were playing equilibrium. Okay, but so they look at the tails. They didn't look at the whole distribution, which is what the theory makes a prediction about. Okay, if they had looked at the whole distribution, they would have realized that there's actual plays too close to expected play. Okay, and therefore their data is inconsistent with mixed strategy Nash equilibrium. Indeed, the behavior of students is largely closer to equilibrium than it was for soccer professionals. Okay, let me talk about one more artifactual field experiment. This is a paper that I wrote with Matt Van Essen that's trying to get at the same issue. Is there a sense in which experience in the field translates into behavior in a laboratory setting? Okay, and here we designed an experiment where the experimental game was designed to be familiar to the game that the subjects had experience with, right? This is unlike the Plascher-Huerta-Wohlig experiment, right? The Plascher-Huerta-Wohlig experiment is taking soccer players, their experience is on the soccer field, kicking penalty kicks, and they were having them come into the lab to play an abstract normal form game. Okay, so here we're taking subjects who experience playing online poker, and we're having them come into the lab to play a different kind of poker game, a simplified poker game. Okay, so let me describe the experimental game. We call this the blind stealing game. So in this game, there's a player it's a two-player game. There's a player who we call the small blind, who antes one chip. Okay, the second player, the big blind, antes two chips. Small blind and big blind are actually terms that come from poker. Okay, each player is dealt a single card from a 4-card deck that has 1 ace and 3 kings. Okay, player 1 moves first, either folding or betting. If player 1 folds, then there are 3 chips in the pot at that point, and 3 chips have been anteed in the pot. If player 1 folds, then player 2 wins the pot. The game ends. If player 1 bets, then player 1 has to add 3 additional chips to the pot, which would now mean there are 6 chips in the pot. Okay, player 2 moves second. Player 2 either folds or calls. If player 2 folds, then player 1 wins the 6-chip pot. Okay, if he calls, then he adds 2 more players to the pot. So now there are 8 chips in the pot. He adds 2 more chips to the pot, making it 8, and then the cards are compared. And so how do we compare it? This is called the showdown in poker. So how does the showdown resolve? If a player holds the ace, then he wins the 8 chips. Okay, if otherwise, the other possibility, if neither player has an ace, then they both hold kings. In that case, the pot's split equally. Okay, so that's the blind stealing game. It's meant to be a very stylized representation of Texas Hold'em. So Texas Hold'em, 2-player Texas Hold'em has exactly this structure. The small blind, the small blind makes a smaller ante than the big blind. Then the small blind actually has the option of, in actual Texas Hold'em, they can either fold, call, or raise. Okay, and so here we're giving the small blind the option of either folding or betting. Yeah. Okay, so it's a simplified version of Texas Hold'em. Very simplified. It would be nice to have, there's lots of data on Texas Hold'em. You might ask, why don't we just look at data from Texas Hold'em. And the problem is that we don't know what the theoretical prediction is for Hold'em. What does the theory say about Texas Hold'em? It's a beautiful game, but like the theory, no one's worked out the analytics for the theory at this point. Okay, so what's the equilibrium in this game? So in this game, if you have an ace, if you're the small blind, if you have an ace, you should bet for sure. You have the strong card, you're going to win. Okay, but the thing is, you also want to bet with positive probability even when you have the weak card. Okay, so when you have a king, you're gonna lose to the ace if your opponent has the ace, or you're gonna tie and split the pot if he has a king. Okay, so you should actually bet with probability 0.5. So when you have the strong card, you bet for sure. When you have the weak card, you bet with probability 0.5, and this leaves player 2 uncertain about whether you have the ace or not. Okay, player 2, of course, if player 2 has the ace, they should call because they're gonna win. Okay, but if they have the king, then they are uncertain about whether you have the ace or a king. Okay, in that case, they should call with probability 0.75. Okay, we had a simple kind of two-group design. So in one treatment, we had experienced online poker players come to the lab. Okay, so at the time, there was a period in time where Texas Hold'em was very big on college campuses. And the legality of online poker playing became a little bit dicey later on. Okay, but at the time it was legal. And so we had a bunch of experienced poker players, and we could measure their experience by how many hands. We asked them to provide us with a collection of hand histories of hands that they'd actually played online. Okay, and then of course we have a control group, which is inexperienced players. And I'm just going to call those guys, the control group, I'm going to call students. So I'm going to talk about poker players and students, but just keep in mind that all of these guys were actually students. It's just that some of them had experience playing poker. Okay, within each group, subjects were randomly assigned to pairs. Okay, each pair was endowed with 100 chips. Okay, as in Texas Hold'em, they alternated between playing the small blind and the big blind, and they played 200 hands. Okay, at the end of 200 hands, a $50 prize was randomly allocated to one player. A player with n chips won the prize with probably n over 200. Okay, so basically, so why did we do this? Well, we did this so that we would not have to worry theoretically about risk attitudes. Okay, so effectively, when they're playing this game, they're playing for chips. But what are chips? Chips are just probabilities of winning the prize, winning the $50 prize. One player won $50. The other player got 0. He walked out with nothing. Okay. Another issue here that I'm not going to talk about, but which was important at the time, is a player can run out of chips before the end of this experiment, right? You can lose as many, I think you can lose as many as 4 chips per hand. Okay, so before the 200 hands are up, you might have actually lost all of your chips. And now you need to be careful with that, because you need to have the right rule for stopping the game when one player is running out of chips. A simple rule you could follow is just that as soon as a player doesn't have enough chips to ante, then you end the game. The problem with that rule is that it actually affects the structure of equilibrium. Okay, so we chose the bankruptcy rule in a way so that in the equilibrium of the super game, that was a repeated game, in the equilibrium of the super game, it was an Nash equilibrium of the super game at each stage to play the mixture that I described earlier, which is to bet with probability 0.5 when you have a king and call with probability 0.5 when you have a king. So it's a subtle design issue that's important, actually. You need to think about these issues when you design an experiment. Okay, because if you don't design the experiment properly, it affects equilibrium play at the end of the experiment when you're close to running out of chips, but that in turn affects equilibrium play before you run out of chips. Okay, so let me go straight to the results. Not surprising to me at least, is that if we look at betting frequencies, so for player 1, the theoretical betting frequency is 0.5, it's 50% when you have a king. We see that the poker players are far from are far from that. The poker players were betting 65% of the time. Okay? They were betting too often. Okay? The students were betting even more often. They were betting 72% of the time. Okay? So this is far from equilibrium play. Okay? This is in the first 100 hands. Okay? So we would, of course, reject equilibrium theory for both groups of, we reject equilibrium play for both poker players and students. Okay? For the, for calling, for player 2, theoretically you call with probably 3/4 of the time. Actually, for poker players, they're pretty close, 73.3%. Okay, students are are further away. Okay, if we look at the second 100 hands, poker players in the second 100 hands basically play the same way. They don't adjust much. They play virtually the same way in the first and the second half. Okay, students though do adjust. The students actually move towards the poker players, right? Their betting frequency goes from 72% to 65% of the time. Their calling frequencies, it moves less, but it moves in the right direction. They go from calling with basically 80% of the time to only 77% of the time. Okay, but so what do we learn overall? So first of all, we reject equilibrium. We reject mixed strategy Nash equilibrium for both groups, the poker players and the students. Okay. It is the case that poker players, at least in the first 100 hands, they behave in a way that's closer to equilibrium. That may not be very satisfying, but that's all we have. Okay. By the last 100 hands, actually, the students don't. The student behavior. The students move closer to equilibrium in the last 100 hands, but they don't get there. Okay, right. So this point 72 is closer to 72 than 65 is in the right direction. 79 than 77 is in the right direction. Okay, and also, but by the last 100 hands, poker players and students are indistinguishable. So if these poker players may be bringing something to the lab, okay, but they're certainly not. They certainly don't come to the lab, look at the game, okay, intuit what the equilibrium is, and then play that equilibrium. They're certainly not doing that, okay, but they're playing closer. They're playing better, perhaps, than the students, or closer to equilibrium. It would be interesting. We haven't done it, but one could imagine actually having pairing. Instead of having poker players playing with poker players, you can have poker players playing with students, right? And you can see whether poker players do better playing this game than the students. They win. You can see whether they tend to win more often when the poker players are playing students. But I don't think anybody's done that experiment. And let me wrap up. So if you see the Plascia-Suerte-Bowling experiment and somebody tells you that paper shows that soccer players play mixed strategy Nash equilibrium, they're wrong. Okay? It doesn't show that. Okay? That study, first of all, it doesn't replicate, and second of all, if you look at their data, their own data shows that soccer players don't play in a way that's consistent with mixed strategy Nash equilibrium. Okay. Thank you.
Thank you, Professor. Thank you, Professor Udit. We don't have much time. I will take just a couple of questions. Okay.
I have a very sort of naive question, which is that when you are doing the experiment in field, and you don't break it up in terms of 2 halves or something like that when you're doing that in experiment. So if you do that for field also, would you see a change in switching there? And then...
Oh, you mean, what, you're saying field?
Yeah, I mean the actual professionals do
okay,
also
like in the
what you're seeing in the lab, because you're arbitrarily breaking it in 100.
Yeah, true. Yeah, so I think you're asking, like, if we, imagine that we took the data from Hawkeye and we switched it. We looked at the first half of the match and the second half of the match, and we could run the test on each half. I don't think we've done that, but it would be the case that when of course we cut the data in half, we also lose power, right? So we would, I think, have less chance of rejecting the theory on either half when we cut the data, when we divide the data. So you could imagine that theory might work better on the second half because they have more experience. But I think that, I mean, it's an empirical question. I think, the players in our data set are all elite players. They've probably played each other before, and they've certainly studied each other's game. So I'm not sure that we would learn a lot by splitting the data in half. I think what would be more interesting, and along the lines you're suggesting, is if you looked at if we could identify matches where players had never played each other before. Okay, then I think it would be interesting to look at initial play versus, say, in the first half of the match versus the second half of the match. Because then we might actually see, and it would be interesting to see, if we might imagine the theory works better once they've actually come to know the payoffs of the game. I mean, when we test the theory, we're assuming that the players know the game, right? And that's that's the assumption underlying the mixed strategy Nash equilibrium that we've been testing. Thank you.
Any more? One more from the students? Yeah.
Yeah. So thank you for the presentation. Actually, related to that question, that for instance, the difference, say, between the case of the tennis match versus these games being played, perhaps it's easier to make a convincing argument that kind of what's the best response for a player is less likely to be history dependent in this lab setting, and players are more likely to have to take into account, for instance, like they have to get an ace out of the hole if they want to stand a chance at winning the match if it's going badly thus far.
Right.
So kind of how would, say for instance, that play notes, you I think mentioned that better players tend to kind of conform to this randomization better than the others, but perhaps that's because the match tends to go well for them most of the time.
Well, yeah, so there is I didn't have much time to talk about. Couldn't show those results formally. There are some regression results that I didn't talk about in this morning. But yeah, so we have evidence that better players behave in a way that is closer to the theory. They're in particular for men, better male players are less serially correlated than lower ranked male players. Now, so I guess there is a question: is that there, when we obtain that result, it could, the better players, the better male players, maybe are more likely to be playing against other male players who are also better than average, right? Because of the tournament structure. So yeah, so part of that might be part of the explanation. Like if it's not just that I'm better, but if I'm playing against you, you're also better. You're also likely to be more better than not. Okay, so yeah, so that there may be a selection effect there that I don't know about, yeah, or that we don't know about. Yeah. Did I answer your question?
Kind of, but also what I kind of was wondering about is if, say, for instance, a player like Federer or someone who's typically on the winning side, how would a player like that respond to kind of being on the losing side? Say he's a set behind, right? And then does that change the behavior of these top of the line players?
Yeah, I don't know the answer to that question. Like maybe, for example, we might observe differences in play whether a player is ahead or behind. And of course, in our data, we just pool everything together, right? It includes everything. But another way that we know that in equilibrium, of course, you should be serially independent. But in fact, you're trying to win, right? Your objective when you play tennis is not to be serially independent. Your objective is to win the match. Okay, and if your opponent is behaving in a way that's serially correlated and therefore predictable, then a best response for you may also be to be serially correlated. You're trying to maybe match or not match his opponent. If you think about poker, right? when you play poker, you don't want to play. When you play poker, you don't want to sit down and say, "I'm going to try and play min-max." No, you sit down and say, "I'm going to try and take all of your money." Okay, and so that involves me trying to detect patterns in your play, or incorrect mixtures. So yeah, so you can imagine that, you know, the fact that we don't reject the theory for the professional tennis suggests that everybody involved is kind of playing something close to an equilibrium. You know, we know that again, I didn't have time to talk about it in the first talk, but you know, there is serial correlation in the direction of serve, both for men and women, which is inconsistent with the theory. And it's unclear why that doesn't get exploited, right? So but again, humans are very bad at generating random sequences, and probably they're very bad at detecting when another player is not behaving truly randomly. Okay, so the gains to trying to exploit serial correlation are perhaps small, but we see that there's much less serial correlation. You know, women are twice as serially correlated than men. So the gains for men, the fact that the serve is so important in men may actually be driving the reduction in the serial correlation we see for men versus women.
Okay, please.
So we're setting, we have a large amount of data, right? So when we test the theory with a data set of this size, we're really demanding a lot from the theory, because if there are systematic departures, even small departures from theory, we would pick it up in a data set of this size. So I think what we've learned, not just from my work on tennis, but also to some extent from the work on soccer with professional soccer players, is that the very elite tennis players and elite professional soccer players, kickers and goalies, that behavior, in some respects, it's consistent with the theory, so long as, if we're asking about equalizing winning probabilities. So that's telling us that remember, it's the server in tennis whose actions make the receiver, I'm sorry, I got it backwards. It's the receiver in tennis whose actions make the server indifferent between serving left and right. So I think we can say with high confidence that in professional tennis, the receivers are behaving in a way that's largely consistent with theory. Okay, the servers they switch direction too much to be consistent with true randomization. But again, humans, there's a lot of evidence that humans are bad at generating random sequences, or maybe identifying departures from random sequences. So I think what we know at this point is two extremes. We know what happens when we get student subjects into the lab, student subjects who don't know much of anything, perhaps, okay, and elite professional tennis players, and we know very little about what happens in between. Okay.
That's what worries me, because game theory isn't supposed to apply to the top 1% of the human capital distribution. It's supposed to apply generally, and what you're telling me is no, it only applies to people who are really, really good at it. That's not a very useful theory.
I would disagree, because if you look at, let's go back and look at O'Neill's experiment, right? So again, to the eye, O'Neill's data looked pretty good. People were very excited about O'Neill's paper when it was published. Okay, it's just that it doesn't pass the very difficult statistical tests that are required by the theory. So the joker in O'Neill's experiment, the players were playing the joker card roughly twice as often as the number card, which is what the theory predicts. Okay, but they're still far enough away from the 40% mixture that we can reject that they're playing the joker card with probability 0.4. So still, I think the theory's told us something really useful in a game like O'Neill's, where it's not at all obvious how to play. Okay, you take some student subjects, you have them sit down for an hour and play a card game, and actually, lo and behold, the choice frequencies come out to be pretty darn close to the theoretical frequencies. Okay, they don't pass the statistical test, but I don't, I'm not. I'm not, my sense is that game theory, I've been talking about mixed strategy games, my sense is that game theory works pretty well a lot of the time when you run laboratory experiments, but at the same time, you can very often reject you can statistically reject equilibrium play on the same data. So, I think of theory as it gives us a suggestion, but we shouldn't take the theory, we shouldn't take the mixed strategies Nash equilibrium so seriously that we think we can bring in student subjects and have them play the O'Neill game and they're going to play the Joker card 40% of the time. No. The theory is broadly works, and for me as a theorist, I'm pretty happy with that. So when they get macro to work this well, we'll be in much, macro. We're still trying to work anything, still work stuff out. Sorry, my apologies to any macro people here, even if it's true.
Things are getting very interesting, but we have to stop at some stage. So we are very thankful to Professor John Wooders and taking us through that in theory, mixed strategy equilibrium, in theory, and when the players actually play that on the ground or in the field or in the laboratory setting, how they may or may not converge to the theoretical prediction. Okay, so there is the learning, but I firmly back John Wooders on this as a theorist. Okay, and then we can play it up outside also. Okay, so now I think our volunteer has some announcement.
Yeah. May I now request Professor Udabhanu Sinha, our chairperson for today, to felicitate. Sorry. Hello. May I now request our chairperson, Professor Udabhanu Sinha, to felicitate Professor Wooders.
This is the organizing committee and from Delhi to Thank you. This is from the students' placement cell. Delhi School has a very vibrant placement cell, and there are some mementos and some calendars.
Thank you very much.
So I request all of you to join us for tea in the lawn, but our next session will start exactly at 4, so please reach the respective parallel sessions. Okay.